Hello, everyone. Making an audio test. Make sure that my voice is coming through.
Hear you fine, Joao.
Thank you, Dale. Oh, I see Toby also.
Hey, good afternoon. How's it going?
So my video is coming. For those of you that don't know me, my name is João Alves, and I am the chairperson for UComms. Thank you all for coming. It's great to have, at least looking at the registration list, we're going to have a big mix of people joining UComms this year, which is incredible. Before I will proceed and introduce the conference, the edition of this year, I would like to introduce you. I have the privilege of introducing you the director of CMRE, Dr. Catherine Warner, who was so kind and also very keen, I have to say, in joining us, and welcome you to UComms, to this edition, virtual edition of UComms. So without any further ado, I would like to give the floor to Dr. Catherine Warner, director of CMRE.
Okay, thanks very much, Joao. Just checking, making sure everyone can still hear me. Great. Well, usually right now I would say something like good afternoon, Europe, and good morning, North America. But as I looked through the conference list, I see I have good night, Australia and Japan and Singapore, and very early good morning for those on the west coast of the United States, and perhaps later in the afternoon for those in the Middle East and South America. So we're pretty much spread across the globe here, and I think I heard someone was also in Iceland, so we got GMT represented as well. So anyway, it's very hard to accommodate that many time zones, but after almost 2 years of COVID, I think I've started saying there was no such thing as time zones anymore. But thank you all again for dialing in, for attending. As you know, this conference was initiated by CMRE in 2012 and held every 2 years since then. The first two conferences were successful enough that in 2016, we had to go to a larger venue, which was the beautiful Villa Marigala in Le Ricci, where I met you in 2018. And unfortunately, we're not there last year, and still even a year later, we still are not to the point of having an in-person meeting. I believe, you know, is definitely this for the safety protocols, this will have to do for now. But I hope that you will find, even in this format, with the access to the talks and time for conversation, that you will still be able to meet the most of it. This event, first and foremost, signifies the importance of underwater communications as an enabling critical technology in maritime science. And it complements quite smoothly the work that CMRE has been doing, first with the establishment of JANUS as the first digital underwater STANAG, and now its support, the CMRE support to its adoption in industry through the Interoperability Fest, and also some of the advances that we've made in doing securing and encrypting the JANUS waveform, which I think towards the end of the conference, there will be some talks about. But even though the conference is virtual, we have kept the core principle, which is the quality of the contributions and taking the time to openly discuss them. So I know everybody gets tired of these online, it gets a little bit saturated with all the WebEx, but I hope that we found the right balance between the talking of the speakers and then the discussion of the participants. Because we continue to engage the best people in this field, as you can tell from around the world participation, and wanting to discuss the leading edge developments in this really important growing area, unprecedented growth and interest and technical success. We have non-acoustic communications, novel transmission schemes, intelligent adaptive modems, and new ways to implement security. So there's a lot to be coming today and the 2 days after this. I do want to acknowledge that CMRE has a team that's busily preparing for some very extensive experimentation with underwater communications with the Portuguese Navy in their annual exercise, the REPMUS, in September. And in fact, I believe I saw at least Roberto Petreccia calling in from his quarantine room on our research vessel, the Alliance, as they're getting ready to leave next Sunday, I think, for Portugal. And best wishes for that exercise. And there's a lot going into setting up a conference like this, but it's only possible really because of the community effort that's put together for the presentations and the people to attend and discuss. Now, of course, I have to call out two of my team, which is Joao Alves, the leader of this event, and Ilaria Saudella for your efficient support organizing and advertising the meeting. So thank you all for dialing in, and I hope you enjoy the conference. And I really hope I can see you next year, 2022, for the 10th anniversary at the Villa Marigula. Over to you, Joao. Mute.
You're right. Someone should make the T-shirt, "You're muted," will be the theme of 2020, 2021. Thank you for coming and opening the conference. And as a matter of fact, I will pick up on that decision that we had to take in June last year when we decided to postpone the UComms. So it was a difficult decision. A lot of consideration went into it, of course. And the truth is that we did not anticipate being still in this condition and under these constraints more than 1 year after. We do acknowledge that this setup is very far from ideal, very far from what we are used to having in the UComms conference. But all our efforts were indeed in the direction to make the most out of the situation we are in. So we wanted to maintain this very strong bond that the UComms community is known for. And we also wanted to do this event without overburdening your calendars. We know that everyone is pretty saturated with these events and these online conferences. So that was also something that we tried to factor in and try to be as considerate as possible, knowing exactly, like our director said, that we are spanning from the west coast of the United States all the way to Japan and in between Brazil, Europe, Middle East, Singapore. So it's quite a wide span of participation that we have. So for putting this together, as you can imagine, there's a lot to thank. The NATO Allied and Command Transformation that funds the CMRE program of work, and that supports also the fact that CMRE includes and has been including since 2012 UComms as part of the portfolio of work that we perform. The IEEE Oceanic Engineering Society, very important. They're always very supportive of UComms. And the Office of Naval Research, also a long-time supporter of UComms. So they are the first line of support that enabled this conference to happen. Then there's, just like my director mentioned, the staff at CMRE that guarantees the technical support, guarantees the day-to-day running of putting together a conference like this. And then on the scientific side, very important, all the session chairs that and the reviewers that contributed their time to making this conference possible. And they cannot be thanked enough. There's a lot of the success of UComms that sits on the effort of session chairs and reviewers. So a big thank you for the role you play in making UComms possible. Then, of course, the authors, and some of the authors accumulate roles as session chairs and reviewers, of course, but the authors are ultimately the ones that make us gather here together for this 3-day event. So, and speaking about the presentations, I would like to, now going a little bit more in the operational side of things, I'd like to remind you that we set up these for 20-minute slots with the guideline of 10 minutes for presentation, 10 minutes for discussion. And please, we did everything to try to make sure that we engage in this discussion. If for some reason people get shy and no questions come, the authors are more than welcome to further expand on some points of their presentation, enrich the presentation. We certainly do not want a parade of papers. We want to discuss ideas. That's what UComms is all about. That's what we want to make sure happens during these 3 days. And this is why, of course, we never considered putting together an offline event where people would download and get presentations or pre-recorded presentations. So that's why we wanted to make sure that we put together a live conference. Also, for the same reason, that's why we made sure that all delegates, from the moment they register, they have access to all the papers, so they can prepare, they can read if they have the availability, and they can prepare for the discussion during this conference. Also, for that reason, we prepared the book of abstracts that is available for everyone that goes to the UComms website. So I certainly do not want to monopolize the stage, so we'll kick off the technical program of the conference. For your reference, the latest schedule is available on the conference website. It should be version 3, dated from August 30. Just make sure that we are all on the same page. When the time comes, if you want to ask a question, I would suggest to wait until the end of the talk and then raise your little digital hand that you will find in the participant list close to your name. If you raise your hand, the person that is running the session will be able to understand that you want to ask a question, and will ask you to then take the stage at some point. I will also suggest to please mute yourself so that we avoid any echoes. Video on or off, I'm a bit divided. I don't know if there's any value in turning the video off. I like to see the people. Since we are far from each other, there's value in seeing each other's faces. I like that. I would like to adhere to the schedule. Let's try that. If there is a no-show, which I don't expect to be, we will move without waiting. We will try to keep always a small break in the middle of every day session. And I would like also to remind you that we'll be live streaming UComms on CMRE's YouTube channel. If any of the presenters don't agree with this, please let us know beforehand. We have one presenter that asked that not to happen, and we're taking the provisions to interrupt the stream for that presentation. But if any one of you don't agree with that, let us know, please. This will, more than anything, will guarantee for a posteriori viewing of the presentations. So for today, we have 2 sessions lined up. The first one is called New Applications Enabled by Next Generation Water Acoustic Communications, and this was set up by Andy Singer and Toby Schneider. I see them both available here, so I'd be more than happy to hand over to them as they prefer, either Toby or Andy or both, and take it from here.
I can take it, Joao.
Go ahead, Toby.
Okay, welcome everyone. I think we'll just sort of pretty much dive right into this session so we can stick on time. But I think the key thing is here, there's incredible amount that is enabled by acoustic communication. In some sense, it's always an enabling technology, and rather than a means in its own right. So I think we'll see quite a diversity of talks in that domain, especially as it relates to autonomous vehicles. And so without further ado, I think we should jump into the first talk here, which is Variability in Shallow Water Communications Performance Near a Busy Shipping Lane by Mandar, Chitre, and his team. So Mandar, I assume you're presenting this.
I am, thanks, Toby. Let me attempt to share my screen. Right. So I hope that worked. You're able to see my screen?
Yes.
Wonderful, thank you. Thanks, Toby, and hello, everyone. Again, hard to say good morning, good afternoon, or good evening, but well, whatever time zone you're in. So the work I'm going to be presenting today, it's a joint work with Teong-Beng and Gabriel Chua, who are at my lab at ARL in Singapore, and Deane, who's from the Scripps Institution of Oceanography. So over the years, and I'm sure as we will see over the next 3 days in UComms, we have had lots of advances in underwater communications, and what was once considered to be a very hard problem, we have made significant steps in order to be able to communicate in lots of waters. Yet, when it comes to communicating in littoral waters, in places which are shallow with lots of variability and shipping, communication remains a big challenge. Some days you go out and everything works beautifully. Other days you go out to the same places, the weather seems to be very similar and things don't work at all. And it is this challenge, this difficulty that we see because of variability that we have been wanting to understand for a long time. So where does this variability come from and what can we do about it? So in order to understand this, what we did was we set up a long-term test bed a few years ago. In this test bed, we have 4 modems, roughly in about a kilometer by kilometer area, where we also monitor weather, both above water and underwater in terms of measuring currents and CTD measurements and so on. We have a busy shipping lane nearby, so we have an AIS receiver which tells us when ships are passing by and what the ships are, so that we can understand whether they have any impact on communications. And we do continuous recording of ambient noise. So the 4 modems there, we get them to do different things, but the data that I'm going to be focusing on today is a 24-day data set that we collected in July 2018 between nodes B and C. So node B here transmitting to node C, 616 meters. This particular link, the variability we see, is what I'll be focusing on in today's talk. So the area that we're working in has a lot of shipping. So Singapore is a very busy port. We get a ship coming in and out of Singapore port every 6 minutes. So you get a lot of ships coming in. What you see in this plot is every dot here is a AIS transmission over the 24-day period. So you can see a lot of ships passing by and you can get a feel for where the density of ships are. So most of these ships, they don't pass through the links. So node B to node C is where we are communicating. There are a few boats that come in and out of this bay, but not very much. Most of the shipping traffic just passes nearby, and you're looking at roughly about a half kilometer kind of distance where a lot of the boats pass, a lot more boats within about a kilometer of distance. Node B is a bottom-mounted node. So we have the node which sits on the bottom. Of course, not here. It's shown on the surface before we deployed it, but it sits in about 10 meters of water depth, bottom-mounted with the transducer about 1 meter above the seabed. It transmits signals to node C, which is 616 meters away. And node C is a buoy which is moored with a surface-mounted modem with a transducer about 2.5 meters below the water surface. And the water depth near the buoy is about 22 meters. So you have a slope going from 10 meters to 22 meters. The signals that we transmitted consist of 18 to 30 kilohertz band signals with 5 different signals that were transmitted. So you have a hyperbolic frequency modulated chirp, both an upsweep and a downsweep. We had a M sequence modulated BPSK signal. We had a frequency hopping BFSK signal, GNS-like data frame, but in the 18 to 30 kilohertz band rather than the GNS band. And a OFDM signal with about 3 kilobits of data in there. So this signal set was transmitted 10 times back to back every 15 minutes. And we did this for a 24-day period, giving us more than 75,000 transmissions that we received. And the analysis from this is where we will get some interesting insights. So to start understanding this, the first thing I'm going to show you is whether the analysis shows any correlations between them. So the first plot on the top left shows the detection performance. So for the hyperbolic frequency modulated signals for the upsweep and the downsweep. And you can see that the performance seems to be very correlated. The way to read these numbers is the detector output gives you something between 0 and 1, with 1 being the maximum correlation that you might get and 0 being the minimum. We have a threshold of 0.25 or 0.3, depending on the particular data set, where we would not detect signals below it. So you will see this diagonal line, which basically shows that the HFM1 detector output was quite similar to HFM2 detector output generally, but there was quite a lot of variability over time. Same thing with if you look at HFM1 versus M sequence. Again, they are fairly correlated, a little less than with HFM2, but they are fairly correlated. So if you understand one, you can understand the performance of the other. When you look at HFM1 versus the bit error rate that we saw for the frequency hopping PFSK, as one would expect, they are inversely correlated. When the detection is good, that is HFM1 detector output is large, you see a small bit error rate, and when the detection is poor, you see a large bit error rate. So no big surprises there. Again, you can understand FHPFSK performance by understanding the detector performance for HFM1. The last one is interesting, and this is HFM1 versus the OFDM-BR. And what you see here is at high HFM1 detector output, you indeed get low OFDM-BRs. Right? However, as the HFM detector output goes lower, there is a vast range of detector outputs over which the BR performance is somewhat similar in OFDM. And this essentially motivated us to look at two particular signals as far as this talk is concerned, the HFM1 and the OFDM, how they are affected by all the other environmental factors, because HFM2 and M sequence and FHBFSK we can understand once we understand HFM1. So the first thing that we did was we played around with the data. We looked at a lot of statistical analysis. This is a summary from one of the multi-factor analysis we did using generalized linear models. And what this shows you is that for the HFM1 detector output, if you look at what are the important factors, we consider a lot of different factors that may potentially play a role. Now, the three important factors that the analysis threw out, saying that these are the ones that seem to have the largest effect. One of them is time of day. So what time of the day it is. The second one is what we call inflow. So this relates to whether the tide is coming into the harbor or the tide is going away from the harbor. Okay, so inflow indicates it's coming into the harbor. Outflow would indicate the tide is going out of the harbor. So that seems to have a significant impact on the detector performance. And the third is the tide itself, the tidal height itself. So that has a large effect. Now, the other factors which seem to have a small effect, it doesn't necessarily mean that these factors are not important. In some cases, it might be that some of these factors may be highly correlated with these three factors, in which case the analysis will pick up any one of those factors because it does not know the causal relationships between them. For example, if time of day and light was quite correlated, maybe it was the lighting conditions that was important, but it might pick up the time of day. So you have to use that knowledge in interpreting the output. So these are the three factors that were important for HFM1. For OFDM, two of the factors were also important. So tide and inflow and outflow were. But the time of day seemed to be less important in OFDM, whereas the other factor that was seemed to be very important is the ambient noise level in the water. Now we'll come to why this is the case in the rest of the talk. But let's start looking at what are the important factors that vary with time of day, since time of day seems to be an important factor. So these box plots show you signal strength, or RSSI is the received signal strength, as a function of time of day averaged over the 24-day period. And what you see is that generally the signal seems to be a lot more variable during the day as compared to the night, but it also seems to have a lot more signal strength on an average as compared to night. So somehow the performance or the signal strength that we saw during the day seemed to be better than at night. In terms of noise, again, what we saw is during the daylight hours, the noise was more variable and maybe a little bit higher, but not by a lot. What you also see in the noise is at about 7 o'clock in the morning or 8 o'clock in the morning down here, and about 7 o'clock in the evening up here, you see a slight increase in noise. And this is related to the well-known biological chorus that you get in the morning and the evening. But between those times, you had a lot more variability. And you can understand this by looking at the third plot down here, which is the number of ships around. So think of, while this is called a weighted ship count, think of this as some form of a ship count as to how many ships are nearby. The way we do the weighted ship count is to weight the ship by the distance it is from our link. So it's a scaled version of a ship count. So what you see is that during the daylight hours, we have a lot more ships passing by as compared to at night. And that partly explains why you have a higher variability in noise level as well as a higher noise level during the day. But it doesn't necessarily explain why one would expect a better signal strength during the day. And this is something that initially perplexed us, and we started looking at it in more detail to understand why. So to understand why, let's start looking at a HFM1 detector output plotted as a function of time. And I'm not going to plot it over the entire 24-day period, but I'm going to show you what it looks like over a 4-day period, which is representative of what we saw in the rest of the data. So here's 1 day, 2nd day, 3rd day, and 4th day, where you have this sun drawn that is 12 p.m. For that day. So you have a reference as to this is the noon time. And what you will see is you get this pattern of good performance gets worse, improves again, then gets worse for a bit, improves again, and then gets worse. Okay? And this kind of a pattern seems to be repeating every day. So it's not exactly the same, but you basically have the same pattern that the day starts off bad, gets better, somewhere just before noon, it gets a little bit worse, then gets better, maybe gets a little bit worse again, and then by evening, things start getting bad. And we weren't sure exactly why this is the case. So we had to start digging a little bit more into detail. So the first thought here was, well, maybe this might have something to do with tidal variations, because obviously with tidal variations, you get the geometry of the situation changing, the multipath changing, and maybe that has some relation to this, especially with the idea that you have 2 tidal cycles a day, seems to be kind of consistent with the 2 maximas or minimas that we seem to be seeing during the day. So on this, I plot the tidal height. Right? So this is the tidal height. And what you will see is, okay, right at the start, you see low tide, bad performance, high tide, good performance. So far, so good. But as you start moving further, you see that this starts getting out of phase. By the time you're getting here, it is, here's a low tide, good performance. And then here's a high tide, bad performance. So it does not stay in phase. So there may be some relationship with tidal cycles, but that obviously does not tell the whole story. So the next thing that we did was we started looking at what does the impulse response look like. So now I plot the impulse response, and the way to read this plot is on the vertical axis, I have the delay. So this is from 0 milliseconds to 3 milliseconds. And then on the horizontal axis is the M sequence number that we have transmitted. So this is a function of time over the 4-day period. And what you see is you do see variation in the impulse response as a function of tidal change, nothing new in there. But what you also see is this initial arrival that we have, which is the strongest of the arrivals, use some structure in here. So there are patches where you have pretty strong arrivals, and then there are these patches in between where it gets weak, but it somehow seems to split apart. Okay? If you take these regions where it is split apart and you mark them out, I have marked these out into 7 different regions, and you'll see that every time it has split apart, you have a minima in the detector performance. So every time you have the split, you have a minima. So we at least seem to have some understanding of where this minima is coming from in terms of looking at the impulse response. But we still don't understand why is it splitting this way. Okay? To see the split a little bit better, I can zoom into one of these and you can see basically what's happening. So you have a strong arrival, and then that arrival splits into 2 different arrivals with very little energy in between. And each of those arrivals is significantly weaker. If I take this plot and I take 2 different slices through it. So here's the blue slice where I have no split, and here's a dotted red slice where I have a split across. And if I plot that as delay versus impulse response, you can see it more clearly. So you have this blue large single arrival, and this is the dotted one, which is the 2 split arrivals. And in fact, if you look at this arrival, it is roughly double the height of this. So what you are seeing here is a coherent sum of these two. As these two arrivals combine, that's what gives you the blue arrival. That gives you a coherent sum, and so 4 times the energy. And that's basically what's giving rise to the detector performance being really good. The other thing that it helps explain is also why the OFDM performance that we saw earlier, that the OFDM performance was relatively insensitive to this. And that's quite easily understandable because OFDM combines the energy that you are getting over the entire symbol period by using the cyclic prefix, and it picks up energy from all the arrivals. So the fact that it is split or it is a single arrival matters much less to OFDM than it matters to the match filter, which is picking up one particular arrival. So we can understand that, right? What are these two arrivals? Most likely, these are the direct and surface reflected arrivals that corresponds to the geometry that we had. But the question is, why are they splitting and combining? Would it be driven by the geometry changes due to tidal height? I mean, that would be the most obvious explanation, that as the tide changes, the tidal height changes geometry, and maybe it's related to that. If that was the case, we would expect that the same tidal height should always give you the same geometry, and therefore it should determine, the tidal height alone should determine whether you have a split or not. Okay? And we had seen already before that the tidal height was not enough to understand the performance. In fact, we can look at this a little bit better. And what you'll see is, let's say you take this horizontal dotted line and look at the same tidal height. So here's tidal height crossing that line, and here's the tidal height crossing that line. Here's a time when the performance was bad. Here's the time when performance in this case is okay, not too great. Here, if I look at it, bad performance at this tidal height, great performance. So the geometry changes alone certainly do not seem to explain things, but it is interesting to note that you have these exact alternate periods. So every time we cross this line, once I have bad performance, once I'm in a good performance region, I'm in a bad performance region, I'm in a good performance region, and so on. And every time if I'm crossing this going upwards, this is a tidal inflow. When I'm crossing this going downwards, this is a tidal outflow. So now you can start understanding why the statistical analysis picked inflow as one of the parameters that is of interest. That there does seem to be a pattern that the tidal height matters, but it matters whether it's on a tidal outflow or on a tidal inflow. But why would that be a case? So could it be that maybe there are geometry changes because of buoy motion? So the buoy is moored, but it does have some motion around the mooring that it can move. To check that, we looked at what the path length change we require in order to explain what we are seeing, and we require about a 20 microsecond path length change. If you work out the geometry, the buoy motion actually does not explain more than about 10% of it. So that did not seem to give us the right answer. So what else could it be? Could it be sound speed changes because of temperature? Maybe the water temperature changes over the day, and is it related to that? Again, probably not, but again, mainly because the temperature in Singapore, even the air temperature varies only between 26 and 30 degrees. The water temperature varies even less than that. And that would only give you about a microsecond of change for the geometry that we are looking at. So that's not likely. You can also see that if we plot air temperature against on this plot, you'll see that there is not a strong correlation with the HFM detector output. So what else could it be? What else can cause a significant change in sound speed? It's not temperature, the geometry is not changing. Well, it turns out that the very likely culprit for this might be bubbles. So it's bubbles from ship wakes that we believe are causing the problem. Now, what do bubbles do? Well, if you have a void fraction of 10 to the power minus 5, that is sufficient to induce about a 10% change in sound speed, which gives us the required changes that we are looking for. Is this reasonable? Well, we went out and measured what the void fractions were in ship wakes, and we found that they are in the order of about 10 to minus 4. So they're 10 times as high, but this is in the shipping lane. What we have shown in a paper that we published last year in GOE is that a lot of small bubbles from ship wakes can get stabilized because of potentially surfactants or things that coat these bubbles, and they can stay in water for tens of minutes. And as they get advected in and out of our communication channel, a void fraction change of the order of 10 to minus 5 is not unreasonable. So if we go back and look at this, we can understand this a lot better now. So what effectively happens is we have shipping that happens mostly during the day, right? In the morning, you have ships injecting bubbles. Then as the tide comes in, these bubbles are brought into the channel, and this basically damages the communication by evening, because during the day, the water gets saturated with bubbles. Evening, the bubbles come into the channel. The next outflow clears it out a little bit. In the morning, when the tide comes in again, you get a smaller change, basically because now you don't have that many fresh bubbles. So you have a lot of the bubbles have gone out. And so you basically get a smaller time of bad performance. And then again, during the day, as the water gets flushed out, you get good performance. And then in the evening, again, you get bad performance. So this cycle seems to explain all the findings that we have. So in conclusion, key takeaways are that we seem to have a strong diurnal variability because of generation of bubbles, mostly coming from ship wakes. These bubbles being advected in and out of our communication channel because of currents moving to and fro. And then for OFDM performance, the ambient noise from the ship also seemed to matter, and that also gave us diurnal variability. So the OFDM performance is explained by a combination of two, whereas the detector performance for the HFMs is mostly explained by just the bubbles coming in and out. The more important long-term takeaway is that these long-term data sets that we collected are key to understanding the underwater acoustic channel, because you need these long-term data sets in order to really get an understanding of what's happening. So with that, I would like to end my presentation and happy to take any questions. Thank you.
Thanks, Mandar. I think we're close to the end of time here, so perhaps one quick question, move on to the next talk. I think Dale has one, if you want to just ask it. You're on mute still.
Sorry, one of your earlier figures showed the signal strength over time. I just wanted to know if, when you calculated signal strength, if that was just from the peak arrival of from the match filter output, or if it included the energy in any of the other significant paths.
So this is signal strength over all the paths. So we look at the total energy that's being received.
All right, thank you.
All right, well, thank you, Mandar. I think we'll move on to the next talk now, where we've got Viktor Lidstrom presenting polar-coded non-coherent acoustic underwater communications.
Thank you very much. Can everyone hear and see? Good?
We can hear you. Yep, there you go.
Okay. Yes. Today I will present the paper for UComms 2020, which is a contribution to the topic of acoustic underwater communication links. And I will talk about the method that is proposed and also results from simulations and from in situ testing. The outline of the presentation is that I will first introduce the background to this work and then the main ideas. And I will present the method, which is a non-coherent frequency shift keying method, together with a polar code. And then lastly, I will present the simulation and the in situ test results. As you know, underwater communication is quite difficult, and in many applications of underwater technology, it's quite expensive and there's high risk. So many applications choose to use a robust link and actually tailor their application around this link. Also, in particular in shallow channels, quite often they are not SNR limited. but rather they are the main source of interference is self-interference from the multipath structure of the channel. Another point is because of the limited capacity of the acoustic channel in underwater networks, there's a high risk of collision. And the last relevant background is that there have been much advances in the field of error correcting coding. For example, polar codes, which are used in the 5G standard. So the main idea here is to use a non-coherent method because of the robustness, together with time and frequency guards, which is because of this self-interference problem. And we choose the guards based on values that are reported in the literature. And then after that, we choose the FSK method, which optimizes the information rate, and apply a polar list decoder. In particular, we will be interested in short frame lengths because of this problem of collision in underwater acoustic networks. So the method is parallel frequency shift keying, where based on literature, I have chosen a time guard of 10 milliseconds after each non-coherent symbol and a frequency guard which is 1 meter per second, and then you change this to the relevant hertz depending on the bandwidth that you're using. And this choice, which is done a priori, is based on literature and should be sufficiently conservative to lower ISI for shallow channels. So there are two design paradigms. Either because of the guards that you put in place. Either you choose a number of frequencies to get the best information rate, or you choose for a 4 frequency shift keying, 4 FSK, a certain number of them in parallel to get the best information rate. And this is because of the time and frequency guards. So on the left, I'm showing an information rate plot for normal FSK, MFSK, and on the right, I'm showing one for 4 FSK, and the x-axis is the number of this 4 FSK in parallel in frequency. And as you can see, there are several choices of number of carriers in the regular FSK, and several good choices of parallel 4 FSK, number of parallel 4 FSK. So for these guards that I have specified, the best choice was 32 FSK and 32 parallel 4 FSK for a code rate of 1/2. And the bandwidth is 10 kilohertz, based on the guards that are chosen. The receiver model is that symbols are estimated with the Fourier transform, and the model for each subband is that there is one amplitude component plus a Gaussian noise component, which is the non-coherent model. And the statistical model for each of these subbands is that they are Rice distributed. Of course, if the amplitude is 0, then this reduces to a Rayleigh distribution. We expect the amplitude and the variance of each subband to change over time, and normally you would need to estimate these before and probably after the frame and interpolate them with some type of pilot scheme. Before the decoding phase, we recalculate the symbol likelihoods to bit likelihoods by summing the symbol likelihoods over the symbols that contain this bit in its alphabet label. The polar code that is used is essentially the same as in 5G, and there it has the name CRC aided list decoder. And a key part of a polar code is to evaluate the reliability of each code bit before choosing which bits that should contain known dummy information and which should contain the actual information. There is no explicit algorithm for evaluating this for frequency shift keying, but there is one so-called generic construction algorithm, which is the same as was originally presented in the original paper for polar codes, which was for binary erasure channels for each coded bit. But this construction algorithm still shows a lot about the actual decoder performance or the structure of the decoder, so it can be used here as well. Of course, you use this algorithm to know which bits in the code word are reliable and have a capacity of 1, and which are not reliable, which should have a capacity of close to 0. And the bits that are not reliable are populated with a known value. So for this type of decoder, the list decoder, it uses L parallel decoders or vanilla decoders that are presented in the original paper for polar codes, and basically just keeps the L most likely code words at each step of the decoding process. And it also, in the case of CRC decoder, at the end, you check which path fulfills the CRC condition. And if none of them fulfill the CRC condition, you pick the one that is most likely based on the likelihood. The complexity is L n log n. N is the frame length, and L is the number of parallel decoders. And here we are using L8, so 8 parallel normal decoders or vanilla decoders, and the CRC values 6 and 9. So these are the number of bits, CRC bits, that are in the code word for a coded length of 64 and 1024 bits. And I didn't write it here, but the code rate is 1/2. So here I'm showing Gaussian noise simulations, or results from the Gaussian noise simulations. And because of this being a particular non-coherent method, I'm comparing it to a more traditional convolutional code with a Viterbi decoder. And to keep it similar to the polar code in terms of complexity, it has a traceback length of 8. And the frame lengths are 64 and 1024, like I mentioned, and code rate is 1/2. So there are quite many lines here, but the two that I would like to highlight are these two down here. And so the one with this star, it's 32 FSK with a short frame. Oops, sorry. And the one with the square is a 4 FSK with a long frame. So it's 4 FSK in this type of simulation, but then when using it in the underwater channel, they are parallel. 32 symbols are parallel in frequency. And what is interesting here is that the polar code for the medium frame length has a waterfall behavior once the SNR is high enough. And both frame lengths and the two methods should have both should have good performance in terms of, or it indicates a good performance for both of them if the SNR is high enough. Here I'm showing the field tests, and so on the left is the results in terms of block error rate and bit error rate. For each line, the top value is the block error rate and the bottom value is the bit error rate. And the results are from 2 different sites in the Stockholm archipelago. I will comment on why there are 2 sites. But first, site A is 3.3 kilometers, which is shown here, the blue line, and site B was a bit shorter, 1.6 kilometer, which is this blue line here, and it's in the Stockholm archipelago. First, site A, the interesting results here are, again, for this point here, which is the polar-coded 32 FSK for the short frame, and this one here, which is the polar-coded 32 FSK for the long frame. So what we can see here is that the polar code for both frame lengths had a good performance over this channel at site A. Actually, the long frame did not have any bit errors at all. The convolution codes performed quite poorly, which can be seen this one up here and this one up here. So even for 32 FSK, the convolution code could not really perform well. Then the parallel FSK, the results at site A are all up here, and the reason for this is that the SNR, the method was strictly SNR limited at this range, which is the reason for a complementary test at site B, which is a bit closer, and so the SNR is a bit better. And again, here we can see that these 2 results here, which is for the polar code with n equals 64 frame length and the n equals 1024, so the medium frame length. This one did not have any errors, and this one had a block error rate which was below 10 to the power of minus 2. Yes, and another thing I want to mention is that I haven't shown it in the paper, but I mentioned that the channel spread was about 6 milliseconds at site A and about 1 millisecond at site B. The concluding remarks to make about this is that the time guard of 10 milliseconds was a conservative assumption with regards to the encountered channels. The underwater acoustic channel, together with the hardware chain, was still a challenging channel, and the reference code performed quite poorly. And with regards to the polar code, the block error rate was always less than 10 to the power minus 2 when the method was not strictly SNR limited. The 32 FSK polar-coded, the polar-coded 32 FSK is of interest for short messages, in particular short 32-bit messages, and the parallel for FSK is of interest for medium-length network messages because it has a higher information rate. And why these 2 coupled could be interested for a adaptive modem because it provides flexibility in the frame length while still using basically the same 2 methods, just change parameters. This is all I have to present. Thank you for listening.
Thank you, Viktor. If people have questions, you could please raise your hand or put them in chat. We'll take them.
I see at least Costas with a raised hand.
Oh, I think that was from my previous from the previous presentation. But since you're giving me the floor as well, may I ask the speaker, did you use any interleaving in your coded modulation schemes?
No interleaving.
Okay, but perhaps that would also that would improve performance in times of correlated fading?
Yeah, this is
Okay.
possible. Yeah.
Okay, thank you.
Thank you.
Yeah, that's actually the same question that Dale has, right, Dale? Or
Yes,
similar?
it is. Same question. And in fact, I'm surprised. My limited experience is I get similar performance from polar codes and the same kind of convolutional decoder that is used in Janus. The polar code seems to work a little better, but not appreciably. So I'm looking for more examples and experience.
Yeah, I mean, I guess it depends a bit on the exact setup of the whole method, maybe. But the experience here was that the difference was enormous. And the convolutional code is quite well known. It's not it's not a strange implementation. Yeah, the exact implementation is mentioned in the paper, or the parameters for the implementation. See, one more question. If I use the same realizations for each of the tests, the same XOR trick, or did I use different realizations? And if so, how do I account for the variability? For the polar codes, it's the same code. The only difference in terms of the CRC check at the end of decoding is the number of CRC bits.
That's not quite what I was asking. So you send a transmission and you get a reception. So that's one realization of the channel.
Yeah.
Now with that one realization, you can use an exclusive OR on the transmit and pretend that any code you want was being used on exactly that realization by putting a one-time exclusive OR on the transmit and receive side. Did you do that, or did you have different realizations for each of your transmissions for each of the codes? So you're comparing a convolutional code and a polar code. Did they have exactly the same channel realization, or was one a few seconds after the other?
Yes, they were. Sorry, not to. I know the problem that you're referring to, and I agree that it is a problem that you send like for one method and then you send the other one afterwards, and the channel might be different. And also here, I for each measurement I put the equipment and then I transmitted one method after the other. But I tried to keep the experiment setup quite stable by using places where there are piers, floating piers, so that the setup doesn't move during the time of the experiment. But I agree that this is a problem when comparing methods in situ.
Right. So there's a way around that. I have a paper with Grant Deane and Jim Preissig that you could take a look at that shows how you can use exactly the same realization. It's for analysis purposes. Obviously, you can't see the ocean twice, but if you pretend that there is an exclusive OR with a one-time pad on the transmit and receive paths, you can actually reuse the same realization. I'll put the link to the paper in the chat. It's useful for these when you want to try and do an a posteriori sort of hindsight analysis of what codes would have worked well. It's a good way to do that.
Yeah, thank you very much, and I'm very interested. Also, in the future I would actually be interested in trying to do this comparison also in watermark, because then you get a more similar comparison between the two methods and codes. But I will definitely look at it. Thank you for your suggestion.
Okay, thank you, Viktor. I think,
by the way, I was just saying it was presented in the previous UComms, by the way.
Sorry.
That's right. That's right. It was at the last UComms. That's exactly right.
Great, thanks, Viktor. I think we should move on to the next talk here for the sake of time. So next up, we have non-data aided estimation of time-varying multiscale Doppler in underwater acoustic channels by Francois-Xavier Socheleau. So Francois, you want to take it away?
Yes, hello everyone. Can you hear me? Can you see my slides?
Yes.
Okay, great. Okay, so in this talk, I will present a method to estimate time-varying Doppler scales resulting from strong accelerations. And this without any preambles or pilots and possibly in multiscale multi-lag channels. So as you all know, the motion-induced Doppler effect compresses or delayed signals in time, and a large number of papers have been published on that topic, but it's still a problem in some cases, and especially in high mobility scenarios. So as shown in this schematic representation, the Doppler effect can be visualized by the time fluctuation of the delays of the channel passes. So this is delays, absolute time. There are 3 passes here. So if the channel is a single scale multi-lag, all pass delays fluctuate at the same pace. And if not, we say that the channel is multiscale multi-lag, which is the considered scenario in this work. So most of the time, the Doppler scale is assumed to be constant over the observation, which may not be accurate in heavy sea conditions, for instance, or let's say for AUV communications. So we will consider possible time-varying Doppler scales. Also, most works make use of preambles or superimposed pilots, which has a cost in terms of data rate and which cannot be exploited in a non-cooperative context. So I will here consider a non-data aided approach. And finally, the methodology that I'm about to present is sufficiently general to be applicable to several types of modulation. So to set the notations, xt is the transmitted signal at reception. So if we consider a multiscale multi-lag channel, the received signal RT is a noisy linear combination of delayed, phase-shifted, and time-warped versions of the transmitted signal. And the time warping functions here model the Doppler effect, which is usually represented as the sum of dominant term that is compensated at reception by a resampling, plus some residual Doppler shift, well, that can be tried with all sorts of narrowband processing. So here I focus on the dominant term and model it as a second order polynomial. So here V is homogeneous to speed and A is homogeneous to relative acceleration. So our objective is to estimate these time warping functions without any prior knowledge on the transmitted symbols. However, we assume that we know the modulation type and the symbol rate. So where is the magic? The magic is in the cyclostationary features of communication signals. So cyclostationarity refers to signals which exhibit periodicity in their statistics. So for instance, PSK, QAM signals are cyclostationary. The periodicity is induced by the use of a constant symbol rate and a pulse shaping filter. CP-OFDM is also known to be cyclostationary thanks to the redundancy induced by the cyclic prefix. And there are plenty of other examples. So here I'll focus on the second order cyclostationarity. So I need to define the autocorrelation function. So it is defined as follows. T is the absolute time here, and U is the lag. So if the signal is second-order cyclostationary, it means that this autocorrelation function is a periodic function of time t. So it can be decomposed as a Fourier series, where the Fourier coefficients can be obtained by computing the cyclic autocorrelation function, okay, which is simply the Fourier transform of the autocorrelation function. And alpha here denote the cycle frequency. So in the first part of this presentation, I use the QPSK signal as a running example. So here you see the in-phase and the quadrature component of a realization of a QPSK signal as a function of time. If we compute the instantaneous power of it, we get some kind of, let's say, pseudo-periodic signal. But actually, if we take the expectation of this, so if we average it over an infinite number of realizations, we get a truly periodic signal. It is a cosine plus some DC component. Okay, and this corresponds to the autocorrelation function at lag 0. And if we take the Fourier transform of it, we get the cyclic autocorrelation function. And we see peaks at -1 and +1 over Ts, where Ts is the symbol duration. So fine. So how is this periodicity affected by Doppler? So if we consider an ideal scenario where there's no drift of the delay, okay, the cyclostationary feature doesn't change at reception. We still get a cosine signal here. Now, if there's a constant drift, okay, the signal remains cyclostationary, but the period of the cosine changes because the perceived symbol rate at reception changes. And if this drift is not constant anymore, we get what we call a time-warped cyclostationary signal. So in our case, the cosine becomes a chirp signal. So the period changes with time. And if we generalize this analysis to a multiscale multilag channel for any PSK or QAM signal, this autocorrelation function becomes a linear combination of several chirp signals, okay, with possible different chirp rate that will depend on the relative acceleration, and possibly different starting frequency that will depend on the relative speed. Okay, so that's for the model. Now, how can we estimate these time warping functions? First, let's go back to the single scale scenario. And if we do the maths, we can show that the time warping function is the one that maximizes the projection of the autocorrelation function on a chirp basis. Okay, but in practice, we don't have access to this autocorrelation function. Okay, because we just observe a single realization. In short, we cannot get access to this signal, but we can access to a given realization. So what we do is that we replaced the autocorrelation function by an unbiased estimate of it, which is simply the instantaneous power here in this example. Okay, so then we use the parametric model for the time warping function, and the cost function simply becomes the inner product between the instantaneous power and a linear chirp that depends on speed and acceleration. So we want to maximize this cost function. An example obtained with bellhop is shown here. So it's a shallow water example with a single Doppler scale. So this is the cost function, acceleration, and speed. And you see that there is a dominant peak here that reveals the true value of the speed and acceleration that was used in this simulation. Now, when the channel is multiscale multilag, the idea is to iterate over this procedure by using a matching pursuit approach. So as I mentioned previously, in this scenario, the autocorrelation function is a linear combination of several chirp signals. So first, we estimate the parameters of the strongest chirp signal by computing the cost function I just talked about. Okay, so in this example, you see here that there is a local maximum. Once we have estimated these parameters, we can subtract the dominant chirp from the observation here being the instantaneous power. Okay, so we have estimated the first Doppler scale, time-varying Doppler scale. And then we see two other local maxima, and we iterate over this procedure to estimate the second Doppler scale, and then the third one. Now, in terms of performance, so here is one example. You can find additional results in the paper. So here we consider a deep water multiscale multi-lag channel with a transmitter moving vertically. So such a configuration is known to be difficult for communication systems because the time-varying channel is mostly made of two passes with similar amplitudes and opposite sign Doppler scales. The performance metric is the root mean square error of the estimate of the time warping functions. And in this example, there are two warping functions because we have two different Doppler scales. Okay, so for this simulation, I still used a QPSK signal. The observation duration is set to 1 second, the baud rate to 5,000. And speed and acceleration are randomly drawn from this range of values. Okay, so in green, this is the performance when we assume that there is no Doppler. So this is the performance as a function of SNR, which is obviously very bad here. In blue, this is the performance of a state-of-the-art method that can handle acceleration, but that do not take into account multiple Doppler scales. And in red, this is our cyclostationary based approach. So this figure shows that it can be quite efficient in multiscale channels. As you see, the asymptotic regime is reached for value of SNR as low as 2.5 dB. Now I'd like to take a couple of minutes to illustrate this idea with real data, so as to show that it is not just a theoretical approach, and also to show that it can be applicable to other types of modulation. So here I used OFDM data acquired in shallow water with heavy sea conditions. And if we adapt our framework to CP OFDM signals, we can compute a cost function that reveals the value of the relative speed and acceleration. Okay, you see here there's a local maximum. And now you'll see these values evolving over time with a time step set to 0.1 second. Okay, so here we go. So once again, this is real data. So you can see that occasionally the acceleration is very high, so -2 meters per second squared. So here this is mostly due to the sea condition and to the fact that the transducer was mounted on a rigid pole, which amplified the ship movement. What's also interesting in this data set is that the distance between the transmitter and the receiver was just a few tenths of meters. So we are in conditions to observe multiscale Doppler. You see here there are two local maxima. So to conclude, so I've just presented a non-data aided method to estimate time-varying Doppler scales in multiscale multi-lag channel. So you can use it in a non-cooperative context or as a complementary method to, let's say, I don't know, preamble-based approaches. Detecting multiple scales may be useful to trigger specific processing, such as multi-rate receiver. You may want to change the waveform, or you may want to filter passes with different scales. I didn't talk about complexity, but it is actually quite reasonable. So for PASK QAM signals, we can implement the cost function using chirp Z transform. So this is just FFT-based implementation. And this framework is applicable to any cyclostationary signal. Be aware that it induces some latency because it is based on block processing. There are plenty of possible perspectives. The performance can be improved by, for instance, considering several lags in the computation of the cost function. We could also consider higher order of time-varying delays, such as jerk, jounce, etc. But it has a cost in terms of complexity. And this framework can also be adapted to impulsive noise scenarios. And that's it. That concludes my presentation. Thank you.
Thank you, Francois. If anyone has questions, please raise your hands, post them in chat.
Can you see the hands raised, Toby? I see 3.
Okay, well, I didn't see what order they're in, so we'll just go up from the bottom. Paul, you want to ask a question?
And Rowie. I see Costas, Neil, Judel, and Rowie.
Okay, shall I ask the first question?
Yeah,
yes, Paul, go ahead.
Yeah, well, it was a very interesting presentation. I do need a little more time to digest it, so I will take your paper and read it afterwards. But I wonder, did you compare your real data experiment? Do you have any ground truth? Because we see the movement in the plot of velocity versus acceleration, but how well does it correspond to the real movement?
That's a good question. No, I haven't got any data on the real movements. What I did is I also measured the speed and acceleration with bank of match filter. Okay, so in a fully data-edit context, and the values are very similar. But that's all I've got so far.
Okay, but that was the question that I wanted to ask. But keep on the good work.
Thank you, Paul.
Rowie, you want to ask your question?
Sure. Hi.
Hello, Rowie.
Work I did on estimating the acceleration of Doppler showed that it is much more sensitive to multipath, variations of Doppler in multipath. This can actually be checked in simulations, right? When you have like a channel impulse response or something. What do you think about that? How would the cyclostationary method work with changes because of multipath?
If I understood well your question, sorry, there's a feedback of sound. So, as I mentioned in my presentation, this method can handle multiple Doppler scales. Okay, you can have a different acceleration from one path to another, so it can take care of it.
The question, I guess, is that you have on the same signal, because of multipath, you have different kind of acceleration values.
Yes.
That creates a problem if you are doing, let's say, the regular way, not the cyclostationary way.
Yes, but with this method, you can estimate the acceleration on each individual path if it is different. Well, obviously, there's a finite resolution. Okay, it depends on the observation duration, on the type of signal, the modulation, the cyclostationary features. But if the acceleration is sufficiently different from one path to another, you can estimate both values.
Okay, so we're about 20 minutes there.
There's costs, and there are 2 questions in the chat also.
Sure, how much do you want to keep it on time versus handle all the questions?
Let's get a couple more.
All right, Costas, go for it.
Thanks. Very interesting work, Francois. If I want to put it in the context, let's say that I want to use these estimates of Doppler in, for example, if I'm running a DFE, then to my understanding, if I understood your work, you could just take the received signal, then you could estimate the Doppler and then subtract it or compensate it and then run the DFE. Is that how you would use it in a DFE?
Well, the question now is how do you use these estimated values? So there are some work on this approach. I know that some use a multi-rate receiver. Okay, so you compensate the Doppler by resampling, let's say, with the value of the main tap. Okay, and you combine it with the resampling value that corresponds to other taps, for instance. There are also equalizers that take care of multiple sampling rates to handle different Doppler values.
Yes, thank you.
Neil, do you want to ask your question? Okay, well, Neil has a question. I've usually found cyclostationary methods to be very sensitive to ISI filters for PSK. Did you use any?
Okay, so the transmit filter is a root raised cosine filter, and this is correct. The cyclostationary features depends on the roll-off, for instance. So the roll-off in these examples was set to 0.5. But if you use a smaller value for the roll-off, the cyclostationary peak will be much lower. Okay, so it does depend on the transmit filter, if it was the question.
And then we have one final question from Monica, if you want to ask your question. Okay, well, the question is, how many multipaths and scales will be enough to model the...
Oh, go ahead.
It's
a good work. I just want to know.
Hi, go ahead.
How many these scales and together will be sufficient? Am I audible? Hi, am I audible?
It's a little unclear, yeah.
A lot of cuts. It's better to read it out in the chat. Sorry.
I can read the question and you can follow up in chat. So how many multipaths and scales will be enough to model the real data?
I'm not sure I understand. For me, this question relates to channel modeling and not specifically to the method I just presented.
Let's clarify in chat, I guess, during the break if you want, and move on to the next talk I think, at this point. Thank you very much, Francois. It was interesting.
Thank you.
So the final talk we have before the break here is from the long-range channel in the ocean to the short-range and very shallow water acoustic channel in ports and harbors. Fabian Steinmetz and Bernd-Christian Renner.
Yes, thank you. I hope you can hear me. So, yeah, thanks for the introduction to my talk. Yeah, perfect. During my talk, we will go from the long-range channel to the short-range channel in ports and harbors. And the motivation or the idea about it that in the future there will be a lot of stuff also inside robotics. So the idea is to bring all the IoT devices inside robotics. So for example, here, you can see it here in the picture below. There's a ship and there's a ship inspection. And in addition to that, there are some sensors which collects data. So for example, pollution data, salinity, temperature, and transmit it in a sensor network to other devices. In addition to that, we will have some micro-autonomous underwater vehicles. We will have some surface vehicles. And here's also an example, which is the RoboVAS Cloud, which stands for Robotic Vessels as a Service, which was a project to check if it is possible to have robotic-aided services in this in port areas, for example. For all of these services and all of these use cases, we need a stable communication above the water and also inside the water to connect, for example, sensors and vehicles and other devices. And all of this communication is typical acoustic communication. And here's a second example where are some sensors deployed at the bottom over an area, also to measure something. And above the water, there is an ASV which collects data from these sensors. So here on the right side, you can see a picture. And we use such a small autonomous vehicle in the lake in Germany to collect data underwater. So it's quite important to have a stable link for these devices. So let's come from the ocean to the ports and harbors. So during the previous research on all underwater modems focused a lot of long-range channels and uses high depth. So for example, in the ocean. And in addition to that, they are quite expensive and have a high power consumption. And opposed to shallow water scenarios, you have a moderate multipath propagation. Opposed to that, in sensor networks, as described before, and also for small devices, you have a medium range and you have shallow water scenarios. And it's quite important that they have a small size and low cost and also low power consumption. And in these areas, we have a high multipath propagation. So to give an example here, on the right side, you see our Ahoy modem, which was developed by our research group, and it's quite a small acoustic underwater modem. And the benefit is that everything is in open source. So you can go to our website here and download the schematics and also the firmware for the modem, and in addition, also the software and the driver. And it provides up a communication range with up to 300 meters and data rates up to 250 bits per second and the default setup, but it's also possible to have higher data rates up to 4.7 kilobits here. But it's still an ongoing research topic, and this is the motivation behind my talk here, to get more information and get deeper in this short-range channel with low-power devices. So let us talk about the acoustic underwater channel. I think during the first talks, we have a lot of discussion about it. And I think you all knows that there's a high multipath propagation. So for example, here, if there's left small underwater vehicle wants to communicate with the second one, there's a direct propagation path. And in addition to that, we have reflections, for example, at the water surface, at the bottom, at key walls, ships, and so on. And in addition to that, we have additive acoustic noise. So the received signal here on the right side is a folding between the transmitted signal and the transmission channel H. And at the end, we add some noise here. So in general, it's really, really important to have a channel knowledge to design new communication schemes, because it's not an AVGN channel, it's a multipath propagation channel. And as I said before, previous research focused the long-range channel, and during the next step, I will focus the short-range channel in a port or in different port areas. So to do this, I will use a classical channel sounding. So the idea of a channel sounding is to give an estimate H hat of the channel transfer function. To do this, you can use, I think everyone knows it, different probe signals with good correlation properties. So for example, pseudo-random binary sequences or linear frequency modulated chirps, which are transmitted. And on the other side, you can record these signals and afterwards you can give an estimate of the channel transfer function. And we can see here on the right side the power delay profile, which is an integration over a longer time period here. And we can see here directly at 0 milliseconds, for example, the arrival of a direct path. And directly afterwards, there's a second peak. So hopefully you can see my cursor here. And there's a second arrival directly afterwards and a third arrival, which is the surface reflection, and afterwards is the bottom reflection. So let us go outside and check this in different scenarios. Of course, it's quite important to say that this channel sound is just a snapshot from this specific area at this specific time. So as we heard in the first talk, there are a lot of changes in between. But however, in this talk, I just want to give 4 examples at 2 locations, because this is quite interesting. We go a lot of, when we go outside, we have 2 typical areas where we did these evaluations. And one area is just possible to access is during the winter. And in the second area, it's also possible to do some measurements during the summer. And during this, we found out that in one area, the packet reception rate in a lot of scenarios are definitely better compared to the packet reception rate in other in the second area. So we will go to these areas and do a channel sounding. So the first area is a small marina without many parts in the water. And the second area is an harbor or marina with a lot of boats, key walls, and obstacles. And now we want to compare both areas. To do this, we use USB oscilloscopes to generate and receive the probe signals. We use 100 milliseconds LFM probe signals in the bandwidth from 50 to 75 kilohertz, which is quite high compared to other devices. But this is the communication bandwidth of our acoustic modem. And we recorded the channel for 60 seconds. So let us start here at the first area. You can see here the evaluation area, which have long jetties, and it's quite free. And I think one of these long jetties have a length of 150 meters. And I call the soundings in the paper the plane sounding, because it's here quite near to Airbus. You can see here a part of the landing stripe. And it's quite interesting. It's a marina without many parts in water, and it's a large area with long jetties. So here are the results of my soundings. So first sounding takes place at a length of 27 meters, and I placed the hydrophone 1.5 meter under the water surface, and we have a depth of 7 meters at the receiver and at the transmitter. And what we can see here is a direct path, and just a few microseconds afterwards, if you go near to your screen, the second path arrives. And then during the first milliseconds, there's some additional arrivals. Also for the longer channel in this specific area, which is approximately 80 meters long, and the hydrophone was also placed 1.5 meters under the water surface, and the depth was 6 meters for transmitter and receiver. You just see one strong arrival, or some scattering, but most of the arrivals are during the first 500 microseconds. Then let us go to the second area to compare both channels. So in the second area, there are a lot of small water areas. So, and in addition to that, we have a lot of both key walls and obstacles in the water. And it's a smaller area. And we also did a sounding here in this area to compare the channels. And this is quite interesting. So in this area, the first channel sounding is also approximately 30 meters long, and we placed the hydrophone 1.3 meter under the surface, and the depth at the transmitter was 4 meters and 2.8 meters at the receiver. And also here we can see a lot of different arrivals during the first 2 or 3 milliseconds. Opposed to the other channel in the first area, they are just arrivals during the first 500 milliseconds. So depending, for example, if you want to build a new modulation scheme, depending on your symbol rate, you get some intra or also inter-symbol interference. And there's also on the right side a much more stronger version of it. So here we placed the receiver in front of a chip, not directly before a chip, just a few meters from a chip away or different chips away. And we can see here a lot of reflections coming at 4 milliseconds, which are reflected at the chips. So 4 milliseconds behind the direct propagation path. Then also this is quite challenging to do a communication in such an multipath propagation channel. So if you compare the first sounding with the second sounding, in the second area we have a lot of more reflection. And this is the reason why we have a lower reception rate. And as I said before, it's quite important that this is just a snapshot for this specific area. So in sum, we can say here, the previous research focused a lot on the long-range channel, but on the other side, there's a growing interest in sensor networks and micro-AOVs. And this results in a need of investigation for short-range and shallow water channels, because most of these applications are just 10 meters, 20 meters, up to a few hundred meters communication distance. And in sum, we can say this is that you have a shorter propagation time in the short-range channel. And a lot of cases, not in every case, but in a lot of cases, you have a reflection at the water surface, which arrives directly after the loss path, typically a few micro or milliseconds. So you get intersymbol interference. And in addition to that, you have quite strong reflections during the first milliseconds. Of course, it depends on this on the area, but this is quite challenging. Yes, thank you.
Thank you, Fabian. If you have questions, as usual, please raise your hand or post in chat. So I have a question. I'm kind of interested more about this modem that you're using. That you briefly mentioned.
I can go back to the modem. I think it's the modem.
Yeah, this whole open source software release. What was your I mean, it's obviously a short range modem. What was your motivation to create this over what's out there already?
So the motivation was a few years ago and to establish a communication between micro AOVs. So because the idea is if you want to build a micro AOV, which is quite small and cost efficient, maybe it costs of 5,000 or 10,000 euros, it doesn't make sense to add a modem which has also a price of 10,000 euros and it's quite large and have a low large power consumption. So based on that, the idea was to develop a small modem with a low data rate, but with low power consumption. And I think the size enabled it to integrate it in a 2-inch tube, this modem. So this is the idea behind it for micro AOVs. And in addition to that, also in the area of acoustic underwater sensor networks, you have a transmission device for sensor data, but which is quite cheap. So this is the motivation behind it.
Yeah, that's great because I see a lot of sort of places where that's becoming increasingly important. Looks like we've got a chat question. Viktor, you want to ask a question?
Yes, I would just like to know for the bit rates that are mentioned here, what are the bandwidth?
Yeah, the bandwidth at the moment is quite large. We use 25 kilohertz because we added a lot of redundancy here, and but this is quite under research. So this is our main research topic to add here some new modulations.
Is it for both the bit rates that are mentioned here?
For both ones. So so the default rate had a lot of redundancy inside you, and we did some repetitions on different frequencies, hopping, and so on. And if we remove all repetitions and hopping, we're getting to a 5-star range. So it depends a bit on the scenario, but the default one is, if you want to just use it, I think it had the highest redundancy and the most of repetitions here. but in both cases, we have the same bandwidth.
Okay, thank you.
Costas?
Thanks. Yes, Fabian, given that the tunnel that you are studying in a port, in a harbor, is very challenging and quite different than those that we are used to see in open seas, in open sea environments. Are you in favor of some specific modulation scheme that you would use in this kind of environment? What is your idea about that?
It's not so clear. So currently we're using an FSK on this motor because it's quite simple to implement. But we're looking for some chirp-based modulation, but it's not clear. And there's a second bottleneck at the microcontroller, but you just have the computational power of this Cortex-M4 on top of the modem. So this is, quite challenging. Yes?
Thank you, Fabian. Yes.
Okay, any more questions? Okay, with that, I guess, thank you very much, Fabian. That was a great talk. At this point, I think we have a break in the schedule. We're running a bit late. Gerard, you want to do this for 10 minutes instead of 15, or give a full 15-minute break?
Yes, I was thinking about that, about coming back at 2:50, like just a small comfort break, and go back at 10 to 4 Italian time.
All right, great. Well, I'll see you back in about 10 minutes.
If Dale is around, Dale, we could take this break to test make sure that you can beam your presentation for tomorrow.
Yep.
Okay, so I'll try to share my screen.
Okay, so our next talk here is going to be multiple access acoustic communication in underwater mobile networks. The authors are Christophe, Renner, Pierre-Jean, Bouvet, Antony, Pottier, and Philippe, Forjonel. So, Pierre-Jean, you take it away.
Just a minute. Just time to. Okay. Should be okay now. Okay, so I am Pierre-Jean Bouvet. I am from Isen in West in France. And today I present the work on behalf of one of my PhD students, Christophe Bernard, that defended his thesis last year. So due to the postponement.
I'm sorry, Pierre-Jean, if you can speak up a little bit, I'm hearing you a bit low. Thank you.
A bit low? Okay, we'll try to speak louder. So I just want to say that due to the postponement of the conference, Christophe is not able to present today, so I do that on his behalf. So as you say, this presentation is called multiple access acoustic communication in underwater mobile networks, and this work was partly funded by the Brittany region and Thales Defense Mission System. So, outline of my presentation is the following. First, I will introduce the context and the objective of this study. Then I will introduce the so-called MUHFM. In the third step, I will present the experimental results and finally draw some conclusion. Okay, so underwater wireless data transmission is, as you know, required for many applications in scientific, commercial, or military field. Three transmission modes are possible: radio waves or optical waves for ultra short or short communications. But beyond 100 meters, acoustic waves are the most privileged transmission link, with a lot of constraints in data rate, for example, low wave celerity also that yields to high latency, and many fading effects that makes the underwater acoustic communication channel very severe and challenging. So in the following, we'll focus on the acoustic waves to transmit data underwater. So what is objective? Our work is to provide underwater acoustic communication link to a fleet of autonomous underwater vehicles, stand for AUV, to surface receiver. So each AUV transmits simultaneously in the same bandwidth to the surface receiver. So this is a uplink transmission scheme. We assume up to 5 AUVs that are by definition in motion. And we assume also range below 1 kilometer and relative low data rate, so below 1 kilobit per second, should be sufficient to transmit, for example, the position of the IUV or sonar track results. So if we go to the state of the art, there are two categories. First, what we call the convention-based protocols, like ALOA, CSMA, and all these variants. And on the second category, we have what we call the deterministic protocols, like TDMA, CDMA, or FDMA, for example. In this study, we will focus on this second category. And in a previous paper, we introduced a protocol called MUCSS, Multi-User Chip Spread Spectrum, and we will serve this protocol as benchmark. And in this presentation, we'll detail an enhanced version of this protocol called MUHFM for hyperbolic frequency modulation chirp signal. Okay, let's now turn to the MUHFM principle. So I would say that the principle is quite comparable to a CDMA approach.
The modulation symbol here, it's DIK, is carried by a specific user-specific waveforms, GI, of duration T, greater than the maximum delay spread of the channel in order to avoid impossible interference. And all the waveform GI are mutually orthogonal in order to enable simple matched filter decoding. The specificity of MUHFM lies in the choice of the waveforms constructed from a chirp signal, namely HFM signal, well known to be well adapted to the underwater acoustic channel. The mutual orthogonality is achieved by using, we'll see after, by Simpson methods and also the Gram-Schmidt iteration process. So let's turn to the cross-section process that comprises two steps. In the first step, we construct a family of narrowband orthogonal chip signal indexed by the user number I, and parameterized by the coefficient zeta obtained for a given bandwidth by the Simpson method. So the narrowband family chips here is here CI. In the second step, the narrowband chips are combined with a full bandwidth HFM signal, G0T, and the mutual orthogonality is achieved owing to the Gram-Schmidt iteration process, as described here in the following equation. So you can find more details in the paper. So this is the system model. Each AUV encodes its own data by using differential modulation and generate its own signal, SIT, that go through the underwater acoustic channel, represented here by the multipass time-varying channel impulse response HI of tau and T. And since each AUV is in motion, we have a user-dependent motion-induced Doppler shift effect represented by the scaling coefficient AI of T that depends on the speed of the AUV. From the point of view of the receiver, all the signals are summed up, leading to the received signal R of T that includes multiple effect due to the channel impulse response here, but also Doppler spread, Doppler shift, and finally multi-user interference. At the receiver side, what we do? We first compensate the Doppler of the desired user. For example, for user 1, we compensate the Doppler for user 1. And then matched filter decoding, and finally differential modulation. We obtain here an estimation of the data transmitted by the AOV I. The choice of differential modulation is motivated by the fact that the spectrum and mutual orthogonality reduce both the intercible interference but also the multiple access interference terms, leading to a one-tap equalization process and avoid complex equalization scheme requiring, for example, channel estimation. Moreover, it's not depicted in this figure. We also add a convolutional encoding and decoding process in order to correct transmission error at the bit level. So here you can find more detail on the Doppler compensation scheme with resampling, phase compensation, and finally the matched filtering process, where here the residual bias beta is efficiently removed by the differential encoding process. So you can find also more details in the paper. Okay, so now let's turn to the results. We performed channel soundings 2 years ago in summer 2019 in a roadstead of Brest by using MLS sequence for several transmission range from 65 meter up to 540 meters. This is a shallow water environment with between 10 or 20 meter depth, water depth. Here you can find an example of the Doppler spread function obtained for a range of 200 meters. So we use these probed channels into the well-known watermark simulator, where the position and the motion of each AUV is simulated by adjusting the relative delay here, also the Doppler scale, and also the relative receive power in order to be quite realistic. So that's all for this slide. So as performance metric, we consider the effective data rate here that represents the average data rate per user, widening by the frame error rate. As benchmark, we consider CDMA, also a TDMA with direct sequence spectrum approach, with parameters such as performance of all protocols are identical in the single user scenario. Okay, so this is all the parameters we considered. So it's 4 kilohertz transmission. We use a splitting factor of 127, and you can see that the time boundaries of the HFM signal is exactly the same as the spreading factor. So in the single user scenario, we are exactly the same performance. So let's have a look on the results. This is for the channel sounding in the Bay of Brett. Each AUV has an emulated speed taken between -2 and +2 meters per second. We also add noise, and the noise power is adjusted, such as the phaser user here has a SNR of 10 dB. And if we look at the left figure depicting the frame error rate as function of the number of active users, we can see that beyond 3 active users, the CDMA approach failed, whereas the MU HFM here in yellow is still work, leading to an effective data rate almost constant as the active users increase, whereas the effective data rate of CDMA collapse here after 3 users. As expected, the frame error rate of TDMA is insensitive to the number of active users, but the effective data rate of TDMA decreases as function of the number of users increase, since the propagation medium is divided in time by the number of users. However, we can say that the comparison with TDMA is not totally fair, since we can use higher spectral efficiency transmission scheme than direct sequence spectrum for TDMA. But this requires higher complexity receiver and also time synchronization in order to ensure the effective time division between all the users. So that's the end of my presentation. So let's now turn to some conclusion. So the main contribution of this work is the proposal of a new multiple access scheme called multi-user HFM. So what we can say is this protocol is well suited for multiple simultaneous communication in a real experiment when the users are in motion. We have shown that it is superior to conventional deterministic protocol like CDMA, and we also show that this protocol is superior than the previous protocol that we introduced, the MU CSS, thanks to the use of narrowband chips. So future works as the following. We plan to study the performance of the proposed technique for higher constellation order in order to increase the data rate. And in our results, we assumed a perfect knowledge of the Doppler shift. So we study the impact of non-perfect Doppler shift estimation to the decoder. So that's the end of my presentation. I hope that everybody was able to hear me. And thank you for your attention and for it was me question.
Thank you very much. Do we have any questions? Francois, want to ask your question?
Yes, Pierre-Jean, do you assume any kind of synchronization between users to maintain orthogonality?
No. No. This is totally asynchronous. The only thing we do at the reception side is we detect each users, but we assume no synchronization between users. That's the interest of such approach.
I'm sorry, I'm having a bit of a hard time listening to you. If you can repeat your last couple of sentences a bit louder.
Okay. I was responding to Francois-Xavier that we assume no synchronization for different users. So the only thing we do is at the receive side is to estimate by correlation each user signal.
Okay, thank you. If I can ask another question, I don't know.
Feel free.
Yes, go ahead. I don't think anyone else is waiting.
When you showed your results for CDMA, you have I think a frame error rate of 100% for 3 users.
4 users.
Of 4 users. This is a bit surprising. Can you explain why?
Why? Because we're talking about frame error rate. That means that since you have it's not a bit error rate, so as soon as you have 1 bit which is not correct, the frame is set totally erroneous. That's why you have a kind of waterfall effect. So rapidly you have a very bad frame error rate. Since we are considering that only 1 bit is erroneous, we have the frame is totally lost. But this, if we can also have a look on the bit error performance, and this we don't have this. You have a kind of transition between the when we increase the number of users.
Okay, thank you.
Any other questions? Okay, well, thank you, Pierre-Jean, and we'll move on to the next talk, I guess.
Okay, thanks a lot.
So the last talk of this session is high-speed underwater acoustic communication for multi-agent supervised autonomy. It'll be Arnaud Giraud and a substantially sized team of colleagues here. Arnaud, yes. You want to take this?
Sure. Am I sharing my screen? Yes.
Yes, looks good.
Yes. Okay. So good morning, everyone. So the title of my presentation today is High-Speed Underwater Acoustic Communication for Multi-Agent Supervised Autonomy. And I will cover essentially different types of field tests we've done in 2019 in order to explore this idea of supervised autonomy supported by high-speed underwater acoustic communication. So my name is Arnaud Jarreau, and I'm working with Schlumberger Research in Cambridge, in US. So in the field of oil and gas, what I'm showing on this slide are typical subsea infrastructure that we have close to production zone. These are called drill center. So they are a big metal piece of equipment, fairly big in volume. Typically, this kind of subsea village can span several hundreds of meters in dimensions. And one of the challenge for us is to provide inspection capabilities to inspect these different equipment. It's extremely important for us to, on a regular basis, explore these different equipment and try to understand what is the state of the different pieces, and are we having any defect, or are we making any, are we creating any leaks, or because any failure of this equipment can have a quite drastic environmental effects. So a typical way of doing subsea inspection, so inspection, maintenance and repair, we call this IMR, is ROV based. So we typically need a fairly big support vessel at surface in order to deploy the ROV, sorry. And the reason of the reason why we need a fairly big support vessel is we have all the management of all the mechanism to handle the management of the tether, which is providing power and communication. So we have the tension measurement system that makes sure the cable is not going to be entangled, and we have a big spool of cable that needs to be on the boat in order for to deploy the ROV during the mission. So typically, the optical fiber in this kind of scenario is going to provide data rate of the order of gigabit. So we can provide, as you know, a fairly high resolution video. So provides close-up inspection of the equipment and a fairly low latency. So ROV based is great for real-time control and visualization and close-up inspection. Where it is lacking is in terms of tether measurement and cost of deployment. What we really would like to achieve is reduce the cost of deployment of this system by using something simpler and so smaller number of equipment to deploy. So this is why we have been interested in this idea of supervised autonomy. And in supervised autonomy, we don't have any tether, we don't have any physical connection between the AUV and the support vessel. So the subsea vehicle is partially autonomous, but it provides in real time some feedback to the user at surface. And typically, it's going to provide measurement from sensors. Sensors can be video or can be different kind of measurement modalities. So by not having a physical connection, we can use a fairly light support vessel at surface. And in our experimentation, we have been using an escape vehicle at surface, which was used as a relay for acoustic communication. So the AUV was performing some kind of inspection tasks, was providing information via the high-speed uplink, was able to receive a command and control via low-speed downlink using this surface ASV. And the surface ASV was retransmitting information back to the light support vessel where the support team, where the crew was. So in this kind of configuration, we typically have a much lower data rate because now it's supported by acoustic communication. We managed to achieve a data rate of the order of 100 kilobits per second with the latency, which is also a little bit bigger because of the need of sharing the acoustic channel between positioning and communication, which is about 30 seconds, at least a couple of 10 seconds in terms of latency. So we have been working on what we call the key enablers to enable this subsea inspection approach. The key enablers, we like to say they are based on 3 pillars: the perception, the autonomy, and the data delivery. So we've been working on these 3 aspects. We've been using in all our experiments a saber-tooth vehicle that I'm showing in this slide, but really the same technology can be used on different types of subsea vehicle, like the Huggin or the HMI Aquanaut AUVs. So for the perception part, we've been leveraging on well-known technologies, good camera and good subsea inspection device, SatSense sonar or multi-beam sonar. But we've also been developing our own measurement modalities. We've been developing a methane leak detector, which is custom for our application, and a flyby LiDAR that can take a scan of subsea equipment while the AUV is moving. For the autonomy part, because the AUV will be close to critical subsea assets, and because of the fairly high latency of the acoustic communication, we need some level of autonomy on the AUV. So we've been working on technique where we fuse information of positioning using the USBL at surface on the surface autonomous vehicle, and fusing this information with the onboard IMU of the AUV. We've also developed some algorithm for path planning, where the underwater robot can decide which path to take in order to make the displacement as efficient as possible. In terms of data delivery, which is really the communication part, so we've developed our own high-speed underwater communication modem, with which we managed to prove we could communicate up to 120 kilobits per second at 2 kilometers. So this fairly high data rate can easily provide enough data rate to transmit real-time video, for example. Real-time video within a little bit of latency caused by the acoustic communication, of course. So we started this work back in 2017 with early technology demonstration. Then we switched to integration a little bit. We developed a full software stack and full software simulator where we could simulate both the subsea part and the surface part and make sure everything was well integrated. And in 2019, and I think it was an industry first for oil and gas, was this demonstration of supervised autonomy using this saber-tooth vehicle. In November 2019, we did a technology demonstration with several clients that were invited to witness some mission we did in La Baie of La Ciotat in France. Since this demonstration, we have been focusing on making this technology available, so bringing technology access, and we are essentially providing licensing and equipment sale for this technology. So a few words about the test we've done. So most of our testing was done in the Bay of La Ciotat. La Ciotat is a small city south of France, not so far from Le Ritchie. So we have a bay which is fairly shallow, and a couple of kilometers, I think it's about 10 kilometers south. The depth is increasing, and it's going up to 2 kilometers depth pretty quickly. So this was the equipment we used during this experiment. We had essentially an operation vessel, which was a fairly small boat with a Ukraine at the back. We used this boat to do a launch and recovery of our AUV. We had our underwater vehicle. It was a customly developed saber-tooth vehicle that we fit with our own acoustic communication and our own measurement modalities. And at surface, we used a vehicle called Drix, which is an autonomous diesel vehicle manufactured by Xblow. So we were using this vehicle to communicate as an escape vehicle to communicate with the subsea AUV. Just as to realize, this is the interface that is seen at surface during the mission. So on the left part, we have the autonomy part, which we use for the definition of the mission. So we can say, okay, I want to do a survey of this region, and we can send a downlink for the AUV to start exploring some region of the seabed and do some survey with all the different sensors we have. On the top right is more the perception part with the navigation and the health monitoring of the AUV. And on the bottom right is the data delivery. So essentially here we are showing a real-time video, but it can be another type of data as well. So all this information, they are available at surface only using acoustic communication. There is no physical link between the AUV at bottom and the surface vehicle. And this is typically what the user would see at surface during the mission. So we have the positioning of the AUV, the positioning of the surface vessel, which tries to optimize the quality of the communication by hovering on the location where the SNR is good in terms of communication. And this is an example of a video that we captured in real time. So it's a barge, a sunken barge that we navigate on top of. And this is a typical example of a video that we can transmit in real time using underwater acoustic communication. So we can transmit video. We also showed that we can transmit different types of data stream. So this is a LiDAR acquisition window. So we use this, for example, to set the proper acquisition parameter for the LiDAR, making sure we have no saturation or we have a good gate configuration to have optimal measurement. And we can do this live. So we can send downlink to set the parameter and see the effect of the acquisition directly live on our data stream. And this on top is a video of the LiDAR. So we switched on the camera, and what I'm showing here is the laser beam, which is doing the scan. Same for multi-beam sonar. So we can use the same kind of video transmission to tune the different parameters live during the mission. And what we think is that there is quite a good benefit, at least for our application, to have various sensing modalities. So we try to illustrate this by doing an inspection of a P-38 plane. So in the Bay of La Ciotat, there is an old P-38 plane from World War II, which sank. So on the left is a picture during the operation, and on the right, the picture of the sunken of the wreck. And we managed to do some point cloud acquisition. So using LiDAR on the left or using a multi-beam sonar on the right. So all these data were acquired while the AUV was moving and doing by doing the mission, by doing the subsea inspection. So we have point cloud, we had this high resolution video, and we have a point cloud from multi-beam sonar as well. So we really think that these kind of data are extremely valuable in order to do this subsea inspection, maintenance, and repair. So in conclusion, the goal of this field test for us was to demonstrate this idea of supervised autonomy and demonstrate that we could support this mission using high-speed acoustic communication by providing this information in real time. We use a surface autonomous vehicle as more as a gateway for ACOM and as well positioning, because the surface vehicle has USBL positioning. We demonstrated that we could do supervision, but also alter the missions during the job execution, thanks to the acoustic communication. We proved we can transmit several types of data using this high-speed acoustic comms, data stream from the camera, from multi-beam sonar or LiDAR. And we are extremely interested by this idea of doing point cloud and in future transmitting this point cloud as well in real time. And these are the kind of application we are working on. So before concluding, I really want to acknowledge many people. It's been a pretty big team effort to achieve this field test. So first of all my co-authors, there are many of them shared between Schlumberger, OneSubsea, and XBlue, and also partners that supported quite a bit the realization of this mission, FluidiaDev, SAB, and EVA. I thank you for your attention.
Thank you, Arnaud. That's very interesting. Who has questions?
Hi.
Go ahead.
Yes. Okay. Hi, everyone. So I am quite impressed about the bit rate that you can achieve. Can you specify? This is vertical links, right? Instead of horizontal links. I mean, can you explain a little bit?
So that's correct. So it's a vertical communication. We are communicating between the AUV, which is close to the seabed, essentially, and we are targeting the ASV at surface. So we are using a conical transducer. So the whole game is to have the ASV at surface, which is within the cone of transmission. So you still have effects that signal needs to be equalized, but it's not as bad as horizontal communication, obviously. So we can achieve pretty good SNR, pretty good data rates in this context. Yes.
Could I follow up with a question? Could you specify a bit if it is, can you disclose information about the modem itself, the high rate modem? What is the error correction capability it has, for example? Any physical layer scheme?
Yeah. So we presented the modem 2 years ago at UComms. And the modem is essentially based on a single carrier modulation with a differential feedback equalizer, and it's a custom implementation of a DFE. And we have a custom implementation of ECC, so we use some flavor of polar codes.
Okay. This is because you are interested in short messaging, or I mean, any specific reason why you picked the polar coding?
We tested different approaches. We compare different types of coding, and we found one which seemed to be working pretty well. So we stick with it, essentially. That was during early testing, yes.
Okay, thank you.
Raoul, do you want to ask a question?
Yes, I also have a question related to the modems. Can you disclose the frequency band you used for the acoustic communications?
Yeah, so for the frequency band, we are staying within ITAR because it's it's a US regulation. So the bandwidth is 20 to 60 kilohertz. We cannot go beyond this, as we are developing this in the US.
Okay, thank you.
Question: what is the refreshing rate of the video, and what is the resolution of the video?
The refreshing rate of the video. So we have been working quite a lot on the compression algorithms, because what we realize is most of the compression algorithm, MPEG-TS or this kind of compression, are really made for low latency and high data rate type of transmission for ADSL, high speed internet. Trying to use the same techniques or the same tuning of the algorithms for underwater acoustic, where we have huge latency, is fairly difficult. So we have been modifying quite a bit the default parameters of MPEG-TS to make this possible. So we had to reduce the video. So we have a whole space of parameters that we can optimize. We can go high resolution, but low refresh rate, because at the end of the day, we don't need 25 images per second most of the time. So we can go at maybe 10 images per second, because the UV is moving fairly slowly. Or we can go the other way and have a much faster refresh rate. But in that case, we have to reduce the resolution of the image. So we can kind of tune these parameters depending on what we want to achieve.
Thanks.
Any final questions? Okay, well, thank you, Arnaud. Thank you to all the speakers in this first session. Quite a diversity of interesting talks. So I guess I'll pass it back to Joao at this point.
Yeah, thank you very much, Toby. Thanks to all the speakers that present in this session. Thank you, Toby, for taking care of managing the presentation. So we are now moving into the second session of the day, which is underwater localization, and was put together by George Klivanitis and Andrea Munafo. Andrea sends his regrets for not being able to be here, but George is, and George will take care of hosting this session until the end of the day today. So George is assistant professor at Florida Atlantic University. Most of you will know and heard about him. So George, please, over to you.
Thank you very much, Joao. Can you all hear me well?
Yes, can hear you well.
Awesome. I also want to extend my gratitude to Andrea, who helped a lot co-chairing the workshop. We have 4 papers for this session, which I guess is what keeps everyone from lunch and some people from dinner. So first paper is titled Accuracy of TWR-Based Ranging and Localization in Mobile Acoustic Underwater Networks. And I believe the presenter is Christian, right? Christian?
Yeah, that's me. Just a second. I screwed something up.
Sure.
So perhaps we can entertain a question in the chat for the previous presenter from Andy. How much of the latency is overhead versus through water delay?
Okay, so can you?
We'll leave that for later then. Okay, over to you, Christian.
Okay, so you can hear me?
Yep.
Okay, yeah, I had to. There was trouble. I was a bit early, and so I discarded the allowing the browser to display, and so I had to restart that. Okay, so yeah, thanks for having me here today. So this is actually a work that I'm presenting today that was jointly done with Taras Djimirovic, who is here today as well. Actually, she did most of the work, and I had the honor to present what she did during that time. So from the background, so we are working on kind of underwater IoT, which probably most of us to some extent are doing, but we have very specific applications, as you've probably learned a bit earlier today. So we are in ports here So there's a very concise, narrow areas that we're talking about with a lot of reflections, and it's shallow waters, and it's also relatively short distances, short ranges that we're talking about. Rivers as well, very shallow rivers, and we have static devices, which are symbolized by the modem here, which you've probably seen before, and also mobile devices here, which are navigating around and trying to take mobile measurements. So one project that we are working on has a very ugly acronym here, Autark Beofisch, which I'm not going to spell out because it's German, but the idea is to do monitoring of fish swarms and to identify how healthy they are and what kind of breeding behavior they're exposing given the climate change that we're facing right now. And we want to do that in an automated way by having mobile robots, for example, these Blueroffs that we bought, and in the end we want to cut the wire. So these devices are supposed to be autonomously following the fish, so we're fish stalkers, so to say, and we want to figure out how they're behaving, do some processing. But that's not what's up to today. So today we want to talk about how these devices can actually figure out where they are to enable them in the end to do autonomous navigation. That is the topic. So the hardware that we're using is either these Blueroffs that you've seen before. So this here does no harm really. This is the acoustic communication device that we're using, the hydrophone down here, which you can barely see because it's all black. And then we have the modem built into here. So this is from one of the accessories that you can buy for the Blueroffs. And we built our own hardware into this little tube here, and now it's able to communicate, but it's also able to measure distances. And we'll talk about how that works in just a second. Alternative devices that we've been playing around with is this hippocampus here from the TU Hamburg and Monsoon from the University of Lübeck, where kind of the development of everything that we're doing kind of started 10 years ago, more or less. And here you can also put in a lot of sensors, acoustic modems, image processing, stuff like that. So that's something that you can do, but we mostly use the Blueroff actually. Now you've kind of seen this slide in a different way before. The communication and localization device that we plan to use is this modem here. One reason being that developed it ourselves. So that means that we have full access to it, and it's also relatively cheap, so we can play around with that. But the research we're doing is really limited to this year because most of the functionality that this modem is offering is also offered in a similar way by commercial devices like devices from Evologics or so, like the general function, what you can do with them, like doing communications and doing distance measurements. So this is the kind of ballpark that we're in. And now what we want to do is, or always wanted to do, is self-localization and autonomous navigation. So some time ago, we started implementing a relatively simple distance measurement technique into the modem, which is something that's supported by different devices as well, like the Evologics modems, where we do some two-way time of flight measurements. So the robot here, right, so that would be the robot, and here we have an anchor. You can kind of read that. Most of my PhDs typically claim that they can barely read what I'm writing, so I'm doing really my best, which is sad, but it is. So the robot is sending out a PAL message. That takes some time, of course, and then the response is at some time received. There is some processing delay here, which we call TW for time waiting, so to say. And now what we're actually interested in is the propagation delay for the PAL message and the propagation delay for the response or the received message. We simply divide that by 2, multiply it by the speed of sound, and then there we go, and we have an estimate of the distance. That we found works quite well in any static scenario. So we put a few acoustic modems into the water, we started measuring the distance, and actually the distance measurements that we got, apart from what we think is tilt error essentially, by how you hang the modems into the water, is like just a few centimeters of standard deviation. So that is relatively precise once you know the speed of sound here, which you can sort of easily estimate. Well, we've learned that if you have bubbles and stuff like that, it's probably not so easy, but we hope that in the channels that we're working in, it hopefully works. So now the question is, how do you turn that into a localization or positioning system? And the idea is to save some bandwidth and overhead and so on. So the robot here is just sending out a poll message, and then that poll message is received by a bunch of anchors that you can see here, A, B, C, and D. And then the first anchor, which is A, immediately responds with a response. So by the delay time here, we get our distance to A, right? And then after a delay, anchor B answers here, and then we have the distance to anchor B, because if we know this waiting time that is imposed here, we can just subtract that from the time of flight measurement that we're taking. Same happens to C and D. And then at the very end, we have 4 distances, right? So we have the distances to A through D, then we do some multilateration with the least squares regression, and then we can finally turn that into a position. So that's the idea here. We did that. We went out into the into a little marina in Finkenwerder, which is close to Hamburg. That's what you can see here. This is Fabian, by the way. So he's running the experiment. And we have, this is not exactly an underwater robot, as you can see here. It actually is a robot underwater, but we wanted to have, first of all, a fixed position, and we wanted to reduce the tilt and so on. And we wanted to have, yeah, you can see the antenna here, really, right? So we're controlling this device, and it's not going autonomously, but we're steering it around underwater. So there actually is underwater communication, and there is like a, probably like here and there, we have anchors, right? And we're measuring distances to them. In practice, we had the anchors positioned at A, B, C, and D. We were navigating around. This is what you can see imposed by these triangles here. And then we also had a GPS receiver, which is on top of the device here. And we measured the GPS positions as well. Now, what we found is that these curves, the blue one, which is GPS, and all of the triangles that we have here, they kind of fit, right? But there is a bunch of error. One error definitely is from GPS, because the GPS receiver we were using was not too precise. I think it was several tens of centimeters or even meters displacement, which you can see here. So what do? First thing you can do is you buy a better GPS device. You use an RTK GPS device, do some compensations, and then you have pretty good estimation of where you are, and then you can compare that to the acoustic localization that you're doing. But we really wanted to go one step back and didn't want to have any errors in there. So we, like in the ground truth that we were using. So the idea really was to do a mathematical analysis of what kind of error we are doing, because the problem is the robot here is initiating the distance measurement by sending the pole, right? So the pole is going here, is reaching the anchor. At the same time, of course, the robot is moving by some speed, a velocity v, because it has an angle here relative to the anchor, and a speed. And then the anchor is responding at a later time with a response here. So the robot has moved again, and then we are receiving the entire response. And only at the very end here, we know the distance. And the question is, what kind of distance would that be? Because the robot has actually moved, right? So we are just measured something which is definitely not the distance that it had here or that it had here. And if we apply this localization scheme that we've seen before, it's getting even more dramatical, because we're having a lot of movement. The robot is moving for a few seconds, really, until you can finally do the estimate of where you're going, right? And we just wanted to know how precise is that going to be in the end. So Terra did a lot of math, which you can see here, not going through that. So the question that we try to answer is, if we do a time of flight two-way ranging, this is giving us this distance here, and then this is the distance that we actually should see at the very end here. So this is kind of the distance that we see here after the entire time that passed during this two-way ranging that we applied. And then we have an actual position of the robot, and we have an actual distance. And we wanted to figure out now what is really the error that we're making, just because of that, under perfect situations, like no bubbles, which are important, which we've learned today, no reflections, nothing like that, just really like plain errors just because of the method that we're applying. We have a lot of influencing factors here, like the speed of the robot, the angle of the motion, initial position, of course, or initial distance from the robot to the anchors in the system. We have this little delay in between, and we have, of course, the times that the packets take. Some of these are knowns because we applied the characteristics of our modem that we have, like how long a data packet takes, This is an empty one. We just send header information. This is a packet that has 4 bytes of payload. That's actually this waiting time that's applied. We had different waiting times here to make sure that the entire area that we can cover is 300 times 300 meters. And we assumed a speed of less than 2 meters per second. So we iterated that here for different speeds. And we looked into just the distances. What is the error in the distances that we make? And now for a larger distance, I'm starting on the right here, at initial distance of 100 meters from the robot to the anchor, any of the anchors. That is fairly dependent on the angle that we have. So that is quite clear, right? So if you're moving kind of perpendicular at 90 degrees and 270 degrees, then what you do is you do something like that. And now you have 2 different distances, this one and this one here, and they're pretty much the same, right? There is no much change in this here because this is exaggerating, right? How much you move actually in this direction. So that's fairly zero error. But what can happen here is if you try to go down to the anchor, so that's the anchor and this is the robot, right? If you go down or if you go up, then you have the maximum error. And for that reason, you have a linear dependency of the speed that the robot is moving with. So that is not so much surprising, but the entire delta is already for just 2 meters per second is relatively large here. Now, the final question that we want to answer is, so if we apply the localization scheme that we had before, how dramatic is that going to be? Quite, and it depends on the angle that you are taking. So the plot I'm having here is a 2D plot. So we assumed just a plane, really, because that's easier to display. And we assumed that all the anchors and the robots have essentially the same depth for this study here. What you can see is the minimum errors, the average errors, and the maximum errors. And what you see on here is, for example, this coordinate here would mean that the robot started here. And it could take any angle. We iterated in steps of 5 degrees. And the minimum error at a speed of 0.2 meters per second that the robot achieved, like the minimum localization error, that's displayed in this plot here. The average error is displayed in this slot, depending on the angle, and the maximum error is actually displayed in this plot over here. We looked into quite some details in here, couldn't write all of them down in the paper, and I'm not telling you all of them apparently here. So it's just about what can we draw from that kind of analysis. So the minimum error is relatively low. So before we've seen that the ranging error is really just a few centimeters. And here we can see in the best case scenario, the error is relatively low. You can see here that will be like 30, 35 centimeters error that we can have regardless of where you start. Now, the worst that can happen, and that is actually quite different, is if you are close to this anchor C here, that may be 75 centimeters, even though the distances that you measure to the individual anchors here, they are just in the 1 or 2 digit centimeter range, really. So they add up, really. And the interesting thing that we noted is, this is the anchor that answers first. So the largest error that you make will be to this anchor here, because you are measuring the distance, you have concluded it, and then you keep on navigating, going somewhere. And if you are like farthest apart from this anchor here, close to C, then the error is getting relatively large. If you're close to this anchor here, and the error is relatively small, the worst case error, so that would be in like somewhere here, 35 to 40 centimeters, so that kind of doubles. And the bottom line is, it really matters what is the order of anchors when you ask them what the distance is, that the scheme really matters quite a bit, and that if you're at 70, 80 centimeters, that is quite a bit, because we didn't consider any of the other real-world errors that occur. So it probably makes a lot of sense to integrate an IMU, doing something like that. And this is actually work that we are doing right now. So it really was the idea, if everything's ideal, how well does it work? Right? Okay, so takeaway message is TWR is cost and space saver. It's feasible in static environments, which I haven't shown you, but I can if you're interested in. We can see quite large errors for distance estimates in a mobile scenario, and we need to integrate something to make this more precise if that's really demanded. With that, thanks for listening, and I'm happy to take any questions that you may have.
Thank you very much, Christian. I think Dale has a question. Dale, you want to mute yourself?
Yeah, just a second.
I can also ask the question for Del. So it says, assume you had the USBL on its buoy, which would inform the UUV of both its strains and bearing. How would this impact your performance?
Yeah, so if we had a more advanced system, so that would really improve the situation, of course. So the idea here was that we wanted to have a system that is comparably cheap. So the robot is relatively cheap, the modem is cheap, and we didn't want to increase the costs because organizations that we've been talking to, like the Port Authority in Hamburg, if they want to run such a system, they wanted to have it relatively cheap with little infrastructure, just a few buoys. So that was the bottom line. If we added, of course, USBL, LBL, something like that, this would most likely improve the scenario quite a bit, because really the driving factor that we have here is that we use this two-way ranging piggybacked on data communication, because the assumption is that we're, like, the robot wants to tell information anyway. So you send the packet, you receive an acknowledgement, we exploit this scheme to get hold of distance information. And if you get rid of all that, the delays that you have are going to be very small. So you're probably somewhere in the couple of centimeter error ranges. That is what I would expect.
Great. Anybody else having questions? Please raise your hand or just unmute yourself and ask Christian directly. I have a quick question, Christian. So how this would be scalable for, let's say, 3 or 4 robots under the same number of anchors?
Honestly, not at all. Not really well. I mean, this is really if you've seen the numbers, like sending this poll takes you a quarter of a second, and collecting all the responses is approximately half a second. So if you have multiple robots or even additional anchor points, then you will get a position update maybe every minute or something like that. So latest at that point, you need an IMU or something related, or a completely different system. And this is something that we're working on right now to have I know that there are approaches out there. The guys at Sapienza did some work, for example, where now this is looking at the robot is sending and is collecting information from all the anchors. If you have multiple robots, it's linearly increasing, and that's a bad thing. So the idea would be to have the anchor sending the information, and then that is exploited by the robot. So this is really for just 1 or 2 robots diving around.
Right. And maybe, if I may, one last question. Is there any access currently that you have at the lower level at the physical layer of the modem, so that you could maybe code some signal that you exchange with the anchor, so that you could support multi-vehicle operations in the future?
We haven't done that, but of course that would be an idea that you could integrate that. You could, of course, like this is assuming what I said before, is that each robot is just sending these pings or pulse, and then all the anchors are answering to each of the pings. Because if you have multiple robots and they're in vicinity and can overhear what kind of information they are sending, then you could probably use that to get hold of distance information and use that. So it doesn't have to be a dedicated scheme like this, but using like code division multiple actors or something like that. This is like one of the things that Fabian actually is looking into.
Awesome. If there are no more questions, I think we can move to the second presentation of the session, which is self-adapting under ice integrated communications and navigation network. And I believe Toby is going to be the presenter for this. Toby, would you like to?
Yes, I will be presenting it. Here, let me share my screen.
Yep.
Okay, you see that? Can you hear me fine? All good?
Yep, perfect.
All right, great, thank you. So this is a kind of a perfect follow-on because we're doing something similar but different than what was just presented. And so this work is an integrated communication and navigation network under the Arctic ice with some self-adapting characteristics, what I'll talk about in a moment. And I did this along with the PI for the program, Professor Henrik Schmidt, and his postdoc, Dr. Supan Rendeni at the Massachusetts Institute of Technology. So a little bit of background. This is not a surprise or novel to any of you that we have this very finite resource of acoustic bandwidth for AUV deployments. Because not only are we using it for communications, we're also typically using it for sensing as well as navigation. And under ice deployments are particularly challenging because you have no ability really at all to access surface-based RF, either for navigation in case of GPS or for comms. So what we did for this particular project was create what we're kind of calling this integrated communication navigation system. So we used off-the-shelf acoustic modem, the Hui micromodem, which probably many of you are familiar with. And what we did was sent a single synchronized pulse that provided both time of flight and data. And so what this looked like basically is kind of LBL with data. We did multilateration at the surface, or what we'll call the top side. And then the position update was sent down on the next topside of vehicle downlink as a communications datagram. Now we deployed this system up in the Beaufort Sea in Alaska in March of 2020. Pictures on the right show a few of the components with the AUV, these surface GPS and comms buoys, and the cabling for one of those buoys. And so schematically, what this deployment looked like is we had so a topside operator tent connected over wireless free-wave communications to 4 of these ice buoys. And each of these buoys had about a 90-meter cable to a transmit hydrophone, which is indicated by the square, and 4 receive element hydrophones, the circles. And because we were looking at this effect due to this warm water layer coming in from Bering Strait on communications performance that we presented back in 2016 and a bit in 2018, we wanted to have the ability to both receive and transmit on this shallow layer at about 30 meters and a deep layer at about 90 meters. And this whole laydown was a couple kilometers by a side. And so the vehicle would send a message picked up by, well, hopefully all 4 of the buoys, but at least 2 would provide us with a fix we could use. And then one of these buoys would transmit the data back down, which included the position of the vehicle when it last sent its message, as well as any commands that we needed to send. So looking at the same thing, but in a sort of system components diagram, we had the AUV over here. The core things here with navigation piece, which was Supan's project, this Hydroman, which took the onboard sensors, INS, and upload looking ice pointing DVL. So we were tracking our motion relative to the ice. And then through the comms piece, which was basically source encoding, which is my Gobi project, and then a micromodem, which we were transmitting synchronously here. So we synchronize an atomic clock before deployment. So it's a one-way time of flight measurement. So this message gets sent to up to 4 buoys. We take the position of the buoys using GPS plus the time of flight measured by the transmission time and the reception time difference to do multilateration and send that position back down as a correction. And then the other thing that's going on here on the top side is in the real environment, we're also modeling the expected propagation using what we call a virtual ocean, essentially a propagation model that takes environmental data measured from CTD casts and provides the topside system with sort of an estimate of which of the best paths to take to transmit back down. And I'll talk a little bit more about that in a moment. So those that optimize are doing really kind of looking at 2 questions, one of which buoy to transmit on, which of the 4, and 2 of them had a deep transmitter and 2 of them had a shallow transmitter. So we got a choice, a bit of spatial diversity and also a choice of depth diversity. And then which of the layers to receive on. So we could choose to receive with the shallow or the deep hydrophones. And the metrics we use, and these metrics are being applied to the modeled propagation to make a decision about the actual transmit and receive decisions. Just straight up SNR, which is nothing fancy there. And then this other metric, which is a bit of a heuristic to try to discount multipath paths with close and strong multipath. So places where you have a direct, strong arrival with preferred. We did this by basically adding in this multipath loss factor to the SNR, which weights negatively cases where you have two rays that are of similar strength coming in at the same time or close to each other. And so using, I just wanted to sort of bring a slide back from the past here. In 2018, I presented this network simulator, NetSim, which we used to develop a lot of the system hardware in the loop before we were able to take this to the ice. And what we saw out of this basically was, and we expected shallow receivers to perform well when the vehicle is shallow, and deep receivers to perform better when the vehicle is deep. And this has to do with this shadow zone caused by this new warm water lens in the Arctic profile. And so what we saw in the actual environment, with basically one exception here at this data point, was that in general, those cases held true. So what you're seeing here on the left is the measured SNR as reported by the micromodem. On the right, the equalizer's error, plotted inverse, so high error on the left, low error on the right, so that these curves are visually similar. So we expect better performance in low air conditions, high SNR. And so here we have the vehicle depth on the y-axis. And so in the shallow case, when the receiver is shallow, is these X dots, we see better performance, again, with the exception of this case, when the vehicle is shallow. And then again, it inverts in the deep case where we see better performance with the deep receivers than the shallow receivers. And similarly, when we look at the error out of the equalizer, except in this case, we don't see this inversion, which is not surprising because what matters more for performance is not so much the overall SNR, but the combination of channel effects. So this kind of validates not only the simulated performance to be able to make at least a very high level decision, like a Boolean, which do we use, like shallow or deep, in terms of the actual environment that we deployed in. So then looking at the second question here, a little bit of, is the self-adapting piece useful? We have these four figures, and what we're looking at here is on the left is the deep transmitter at about 90 meters. On the right, the shallow transmitter at about 30 meters. And then for each of these plots, this was done with the fixed buoys, not with the AUV. So each of these was the range between the transmitter and the receiver for the, as I said, deep transmit and the shallow transmit for these two different metrics that I presented earlier, just straight up SNR and then SNR with penalty for multipaths that are close and strong. And so what's on the left is real data, if you will, the packet success coming out of the actual system. And on the right is the modeled but predicted performance metrics using the sound speed profile and the virtual ocean. And so what we're seeing here then is qualitatively, in most cases, these curves follow a similar pattern, but it's certainly not a one-to-one mapping. So in this case, like we see higher MPP value and we see higher packet success and then a lower MPP value and lower packet success, except for this particular case where you actually see them cross in the actual performance, but the modeled prediction is not that way. So this kind of drive home a few things that, my conclusion, the benefits here, we have multiple data streams from the vehicle, which is kind of nice operationally. By synchronizing your navigation with your comms, you're actually receiving this at 3 or 4 points, 2 or 3. So even if you don't get a really high quality 3 or 4 beacon navigation update, at least you're getting data from the vehicle, 1 or 2 of these. And it's efficient use of the bandwidth. You're not spending time to do comms and then spending time to do nav as separate events. And the drawbacks, of course, is a substantial amount of hardware, as I showed on some of those pictures. And this was the piece from the previous slide. I mean, the model metrics do not predict real performance perfectly. They're good enough to make some Boolean decisions. Like I showed, like shallow versus deep, but if you want to make sort of more fine-grained decisions, then I think this is where we need to look into learning approaches, where you can start with a priori modeled predictions, but then as the system's deployed long enough, I mean, we only had this deployed for a couple of days, so really no time to do that. But if you had something out there for weeks or months, you can start trying to adapt to what's actually happening. And then the final piece is that this particular topology requires an additional topside AUV downlink to update the vehicle. So you could switch it if you don't need to track the vehicle topside, but you want the vehicle to have its position regularly updated. You could have the buoys transmit either out of band or using coded signals, and then have the vehicle be the one that calculates the fix using multilateration. So with that, I will conclude and acknowledge everyone. There's a really big team involved in this. There's the micromodem group folks who helped out with development and deployment of the hardware, the MIT team and the GDMS, the vehicle. ASL headed up the whole project at ISEX, and UIC Science is logistics support, and everyone who contributed to open source projects. That, I'll take any questions anyone has.
Thank you. Thank you very much, Toby, for keeping it on time. And I think we have enough time for questions, and we are on schedule now. So again, I see Kostas has a question. Kostas, you want to go?
Yes, Toby, very nice presentation. I just wanted to know a bit more about your motivation to use this PMPP parameter that you're trying to use in order to predict the performance of the micromodem. Why do you need that? You said that if there are two rays of similar power arriving, then you're trying to penalize that situation where if there is only one, for example, you are in favor of it. Did I get correctly? And why you want to go that way?
So the motivation comes from what we've seen out of NetSim. And I mean, this is very much a engineering solution, I guess I'd say, more than necessarily a theoretic one. But if you look at like the error out of the equalizer for micromodem, which generally predicts the packet success, you see the best cases aren't really when you have high SNR, but really when you're getting a single arrival, or again, like in these cases where you have a huge number of surface arrivals, the performance is bouncing all over the place. So there's a heuristic that Henrik came up with. I was actually his piece, so I don't want to talk to tremendous amounts of the motivation behind that, but I think it's something very quick to calculate and tries to draw out some of this performance that we see improving when there's only a single direct arrival and less multipath.
Got it. So, I mean, if you want to kind of extrapolate that, because now this means that it's very tailored to the micromodem and the way it behaves. But if you want to, let's say, do it more generally, you would come up. I mean, you try to put, let's say, the limitations of the modem inside your decision process in some sense. Right.
So, I mean, the metrics here, like we can compute whatever metrics make sense out of this system. So, like if you, and this is where I kind of want to go with. One thing I've seen that's really challenging is integrating the vehicles community with the acoustic comms community, because we have like, I'm not saying like orthogonal mindsets and backgrounds, but they do they're kind of at odds at times. I mean, the signal processing side versus robotics and stuff. What I try to do is segregate those where it's possible to essentially allow people who know the modem performance and whatnot to bring those to the table, and where we can then plug it into the system basically right here. So for particular modem, take that metric that's better than what we've come up with and put that in and use it, I think would be pretty cool.
Okay, thanks a lot, Toby.
Roald, I think you have a question too. You want to mute yourself?
This may be related to the previous answer, but I was wondering why you have to select one of the receiver depths instead of combining them in some manner. For example, running both and using the best or something.
That's just a limitation to what the micromodem exposes to us. So essentially, if we there's nothing in their firmware, which is proprietary, to do a combination that would be reasonable over such a difference in arrival times. So that's a hardware limitation, or I guess an implementation-based limitation, not a.
You will need 2 micromodems in parallel then to do that.
Yeah. But this is basically, so their system is 4 receive elements in a single transmit element, which is how they've designed their hardware, and that was what we had available to us. Again, kind of a whole discussion point of how to go from the theoretical to the in-water, and where that kind of gets lost along the way. Because things like this, yeah, they're just frustrating, not, I guess, real limitations, but they are real limitations if you're going to put stuff in the water.
Yeah.
Perfect. I don't see anybody else having a question, so I guess so that we can keep it on time, we can move on.
May I suggest you have a quick read into the chat? There's a bit of discussion going on that you can bring to the...
Sure. Sure. Thank you, Chua. Yeah. I think Andy replied to Costas that there seems to be a DFE micromodem tailored penalty. A water filling based capacity penalty might be more generic. And then Costas replied back and says, I agree. Also, the Doppler needs to be taken into account as it dictates performance. Would you like to comment on that, Toby?
Yeah, I mean, again, this is a little bit out of my wheelhouse, and I think this would be where I'd love to have feedback. So if you have suggestions on more generic penalties and metrics that you'd like to share, I'd be more than happy to take into account for this future work.
I mean, I could give you a quick, let's say, insight. The equalizer really depends on the multipath spread and the Doppler spread. And in the wireless community, this is called spread factor, channel spread factor. So I mean, this is kind of the product of the delay spread and the Doppler spread. It gives you what is the spread of the signal in time and frequency, and this is an indication of if an equalizer can cope with that or not. So, for example, if the spread factor is very, very low, close to 10 to -3 or less, then you can anticipate the DFE with a good performance. If it is close to 10 to -1, then you can anticipate a bad performance. So this is a very kind of, I mean, that's also a first order approximation of the performance, if you wanna say so, for the DFE.
Great, thank you.
Perfect. Anybody else wanna go? Well, about 4 minutes of the schedule. I guess we can move on. Zoa, what do you think?
Yeah, sure. Thank you.
Thank you, Toby, again. Thanks very much.
Thank you.
The next one in line is myself. So let me share my screen. Can everybody see my presentation? I guess I'll need the help. Zoa,
I can, but it's not on full screen. Yeah, now it is. Yes, thank you.
It is. Perfect. This is collaborative work with a couple of folks. Panos Markopoulos from the Department of Electrical and Microelectronic Engineering in RIT in Rochester. Dimitris Pados from the Center for Connected Autonomy and AI at Florida Atlantic University. And Roy Diamant from the Department of Marine Technologies in the University of Haifa in Israel. The title of the talk is Robust Graph Localization for Underwater Acoustic Networks, and it's kind of changing gears compared to what we've seen in the two other presentations. And this is my background and motivation slide. I guess the previous speakers have done a great job motivating why robust localization is important and actually fundamental to the success of underwater communications and networking. Some examples are location-aware scheduling, data routing, georeferencing of the collected underwater sensor data. On the right, you see some applications of multi-vehicle swarming, where localization could play a significant role to support communication and networking between these vehicles. Traditionally, this is performed at the track node, and some common baseline approaches are using metrics such as receive signal strength indication, time difference of arrival, time of arrival, or angle of arrival. Now, the biggest challenge, of course, is the environment, right? The environment can corrupt these baseline methods due to some type of impulsive noise, due to some Doppler spreading. Non-line of sight multipath could also destroy your measurements or long propagation delays. And at the same time, underwater networks, although we want to talk about Internet of Underwater Things becoming a thing, are mostly at this stage based on sparse deployments that are encompassing usually a few hop connections. So connectivity with all the anchors or the transponders for your baseline might not be an option, might not always be feasible, right? So you might have to end up doing some tunnel fingerprinting or math field processing, which again, if there are medium fluctuations, you would have some type of ambiguities regarding your positioning, right? So bottom line here is that there are position ambiguities that might arise due to corruption of your ranging measurements and due to lack of connectivity, full connectivity in your swarm of underwater robots, let's say. So we've looked into the problem of graph localization, and really this was an idea that came from Roy. He has been looking at that as the problem of localizing distress signals that are coming from divers, right? So we consider that the network of nodes can really be seen as a connected graph, and we want now to leverage the pairwise distance measurements that these nodes have to estimate the relative positions, right? And this has been studied a lot using Euclidean distance matrices. This is a tool that has been used a lot in wireless sensor networks, psychometry, and other fields. The signal processing community hasn't been picking it up a lot. And the cool thing about it is that you can now build this Euclidean distance matrix that you see on the right-hand side. Some of the blocks of that matrix might be missing because there might be missing links, missing edges in this graph. And some of these might also be corrupted due to some additive noise or other phenomena that are happening underwater. So the state of the art on graph localization has been relying on applying what's called the multidimensional scaling algorithm, which is nothing else than doing eigenvalue decomposition on this Euclidean distance matrices and then going back to the coordinates of your nodes, right? So all the nodes are collecting data, pairwise distance measurements to a central processing node. That central processing node forms that Euclidean distance matrix, and then he can apply the multidimensional scaling. There has been other variants of multidimensional scaling that has been studied over the years that had as a focus to improve the sensitivity to errors, as well as cases of outlying or outliers or other faulty measurements, right? And finally, graph localization has also been looked as a convex optimization problem using some proximity induced connectivity constraints. But if we are talking now about networks of a lot of nodes ranging over some kilometers, still the computational complexity for implementing these algorithms in the field might not be favorable. So here's the system model that we will consider for the rest of the presentation. We consider a set of n underwater acoustic nodes. We denote by xi the vector, the d-dimensional vector of the ith node in our set. We define the true square distance matrix of the graph as d, as you see in the slide. Each node can then estimate its distance from every other node that is in close proximity. There can be some protocol that implements that so that every node can have a copy of that distance matrix, right? or you can have these distance measurements denoted, contained in that D-check matrix, which is an n-by-n matrix, gathered in a central processing node. By W, capital is an n-by-n matrix, which takes 0 and 1 values. And this is the connectivity map. So which edges are, the edges that are 0 will denote the edges that do not connect two nodes in the network. Then for every link, then we can write this D-check matrix, which is the distance measurement matrix, as the product of W, which is our connectivity map, right, times D plus E. D is our true square distance matrix, and E is a matrix of the same dimension, n by n, which contains some estimation errors. Right? Now, the goal of this work is to develop a method that will retrieve the coordinate matrix, the matrix X, which is going to be a D by N matrix containing the coordinates of all the nodes in the network. When you give the D-check matrix, the N by N matrix, and you consider that this D-check matrix might be incomplete and might at the same time contain some sparse outliers. So this is the algorithm that we propose. We call it MAD-MDS, which stands for actually mean absolute deviation, multidimensional scaling. So we are still using the multidimensional scaling algorithm, but we are adding 2 more steps at the beginning of this. So given our D-check matrix, which is the pairwise distance matrix, and W, which is again the connectivity map, the first thing we do is to find a way to remove the corruptions or outliers that might be contained in that D-check matrix. The second step will be to complete any missing entries of that matrix using the clean version that step number 1 has given us. And once we've cleaned and once we've completed the entries, the last step would be to apply just multidimensional scaling and see how this works, how good can be the coordinates of the underwater nodes that we recover. So here is a bit more detail, some slides with a bit more detail about it and every step. For computing, for cleaning the outliers, what we do is that we compute actually the median absolute deviation. And why we do that because this is a metric that's proven in statistics to be more resilient than the simple standard deviation, which is calculating the square differences from your mean. So if there is some outlier, that outlier actually will be more emphasized. And once we calculate that median, then we can use it to decide what's an outlying value looking like in that D-check matrix. So we will look overall the entries of that D-check matrix, and we will calculate that difference, DI minus median D. And if that's greater than a constant tau, which usually takes values 8 and 10, based on the sparsity of the measurements, right? Then we will discard this value as a potential outlier. The second step would be to get that clean matrix from step number 1 and just apply eigenvalue truncation and take advantage of the rank property of the Euclidean distance matrices. So what the Euclidean distance matrices tell you is that they are symmetric matrices, so that are of size D by N, and the rank of an EDM for points in RT is at most D plus 2. So what this algorithm actually says is that get that clean matrix, do eigenvalue decomposition on that matrix, keep only the D plus 2 top eigenvectors and eigenvalues, and then do that updating on your D tilde matrix until you converge or terminate, and at the same time set as 0 the rest of the diagonal or negative entries that might have popped up in your D tilde. This is usually found in the literature as the rank-based completion algorithm. So that's the second step that help us do the matrix completion of the clean algorithm. And finally, now that we have that full matrix, full completed matrix, D hat, that step number 2 gave us, we just apply multidimensional scaling, which is consisted of the following 3 steps. You can build G, which is known as the gram matrix, by calculating J as the identity minus 1 transpose over N, where N is the number of your nodes in your network. So you can use that J now to build that G matrix, that gram matrix, and then apply eigenvalue decomposition on that gram matrix. And then you can go back to your point coordinates using the D-top eigenvalues and eigenvectors, right? Now, of course, the coordinates that this algorithm will give you will not correspond to the original ones, but there will be some transformed, rotated, flipped, or translated version. And to align the results of the coordinates that you get, you will have to use some anchors potentially, right? But still, for applications such as scheduling of network node transmissions, relative coordinates within the graph are sufficient, right? But you could solve these ambiguities if you had a set of anchored nodes with fixed and known positions. So for the performance analysis, we did 2 things. We evaluated MAD-MTS through numerical studies on random ad hoc network graphs, and on underwater network topologies from past sea experiments that have been done in Haifa. And the second thing we did is we compared the performance of MAD-MTS to actually state-of-the-art graph localization approaches that are in the literature right now, which deal with missing data or missing and corrupted data at the same time. So here are the results for the simulation studies. We considered a uniform deployment of 5 underwater nodes in an area of 2 by 2 kilometers. We considered 1,000 realizations of 12 different graphs of these networks of nodes. And each entry in the distance matrix, in that Euclidean distance matrix, can be corrupted from low variance 0 mean Gaussian noise with probability 0.9, or with high variance 0 mean Gaussian noise with probability 0.1. The graph on the left shows average root measured in kilometers versus the maximum communication range. This is the range that after which the nodes can communicate, right? In this 2 by 2 kilometers, and we observe that as the maximum communication range increases, the graph actually becomes more and more connected, so the root mean square error decreases significantly. With the blue curve, we see the result of graph localization using the rank-based completion plus the multidimensional scaling, so without considering any cleaning of any outliers. And you see that you get about 0.5 kilometers of ambiguity, even when the graph is fully connected. The second curve is actually a state-of-the-art algorithm which applies cleaning and completion of your distance matrix using robust principal component analysis, and then applies multidimensional scaling on this matrix. And with black is actually the performance of the MAD-MTS algorithm. The second curve shows, again, average RMSC versus distance measurement error standard deviation. So what we did is that we took the network topology from at-sea experiments that have been done in the Haifa port with 4 nodes. These were 4 boats using underwater acoustic modems. We considered the true coordinates and time-varying topology. So the matrix W was actually time-varying. And this was actually a fully connected network, right? So we didn't have any missing entries. Again, we compared the performance of 3 algorithms. The first one is completion plus MDS. The second one is robust PCA plus MDS. And the third one is MAD-MTS. Of course, as the measurement error increases, we expect that the development square error will increase, but we observe that MAD-MTS actually reaches to a flat point of about 0.3 kilometers, even when the outliers are of high variance, which is kind of surprising. That's my last slide. This is a snapshot of the network topology that we evaluated at sea. So with purple, you see the actual true topology. With blue triangles, you see what the rank-based completion plus MTS gives you. And with red and black, you see the result of RPCA and MAD-MTS. This is a snapshot for assuming standard deviation error of 10. So we are expecting about 0.3 kilometers based on what we see on this figure. And if you make the calculations here, you will see that holds true. So to conclude, we considered graph localization both under incomplete and outlier corrupted measurements. Apart from the direct impact that these have to the MTS, we've seen that outliers can also significantly mislead the completion process. So it's important that cleaning step, that first cleaning step is an important step. As next steps, we want to explore how mobility and fast-changing network topologies could impact the performance of these algorithms. And we want to integrate some network initialization or other distance estimation methods to calculate that Euclidean distance matrix and see how faulty measurements or missing links could affect the performance in the wild, in an actual setup in the wild. So with that, I will close my presentation, and I'm happy to take any questions. And
George, I see a question in the chat. I don't know if Roberto has a good enough connection to ask himself, or perhaps you will want to read it out loud and try to answer.
Sure. He says, not sure if I'm missing something, but this seems to be designed for static networks. How can this be applied to mobile networks, moving anchors, or moving AUVs? Yeah. So I kept that for the conclusions. Definitely, there is some overhead that will have to be taken into account in the design of a protocol that would allow this process to run faster for mobile networks. But really, that's something to be done at the protocol level design, right? The important thing that actually struck us when we looked into that from only the simulation perspective was the importance of, I mean, you can't do much when you have both outliers and missing entries in that matrix, right? And robust PCA is the gold standard, and it seems that we are beating that. So how do you treat outliers before you complete your missing entries, or if you do that jointly is really the question that we were after as part of this work.
Sorry, George, it is Roberto. I wrote the question in the chat before your last slide where you say that you will target mobility as the next step. But as you mentioned, so basically the convergence time and the time you need to clean up and compute the output, it will be predominant in how you apply these in moving and dynamic environments. So that was my feeling.
Yeah, and that's something that I don't have like an answer right now, but I think it's something that can be certainly investigated in the future steps of this work.
Thank you.
Yeah.
George, do you mind going back one slide?
Sure. This one? Let me go back to, I lost my camera, so I was looking for my camera.
Let me just have a quick look.
So the black dots here, the black circles are proposed, the coordinates returned by the proposed algorithm, and let's say the squares are actually what RPCA, robust PCA returns, which is much worse, both in terms of orientation and in terms of accuracy.
Yeah, got it. Okay. Thank you. I don't know if there are more questions for you at this moment.
Okay. Are we doing good with time? I think we're 5 minutes over, so should we move on to the last talk of the day and of the session?
Yeah, I think so.
Yeah, okay. So the title of the next talk is Delay-Tolerant Data Fusion for Underwater Acoustic Tracking Networks by Mohammed is going to be the speaker, right, yes. Mohammed?
Yes. Can you hear me?
Yes. Could you please share your screen?
Yeah.
Awesome. Take it away.
Thank you. Hello, everyone. And my presentation is about introducing delay-tolerant data fusion for underwater acoustic tracking networks. I first overview the whole problem and then introduce the scenario, talk about the system model, and then propose fusion methods, and then I overview the results and make the conclusion. So basically,
Reza, sorry, yes. May I ask you to please speak up a little bit?
Can you hear me better?
Yeah, thank you very much. Thank you, Reza.
Yeah, sure. So the scenario that we are considering here is a network of distributed underwater sensors that the goal is to monitor the movement of the object across an area. And we have a bunch of sensors that measure the strength of the signal generated by these objects and convey those measurements to the local fusion centers. And then we have a number of fusion centers. They are deployed over the large area, and then the fusion centers then communicate with each other to achieve some sort of consensus to basically estimate the location of the moving objects. We propose two methods for the data fusion: a partial estimator when the delay in communication between the fusion centers is not negligible. We evaluate the performance in the context of multiple object tracking in extended Kalman filtering, and then we show the performance of the method compared to the case when delay is ignored. So just briefly talk about the background, the previous works. I don't want to go into details, but in the interest of time. But the problem of partial estimators is basically a study in different contexts. Here we consider basically an object tracking, but the similar problem, mathematically similar problem, is discussed in different areas. The fusion centers here can be, basically connect over separate infrastructure that may not share the same bandwidth with the sensors. The delay between the fusion center is the problem of interest and how that affects the final localization. So this a mathematically equivalent problem we have in statistical signal processing, where be interested in extracting the parameters of a model or infer them from a large data set. In those situations, performing a statistical inference to extract a global estimation, in most cases impractical because of imposing computational memory and storage constraints. So the common solution is to divide the data among multiple partial estimators, or the equivalently multiple machines, multiple cores in one machine, and then combine the estimates together to approximate the global. So in this situation, the goal is to find an optimal combination that have the performance as close as possible to a global estimator that have access to all information. So as I mentioned, there are many previous works that has done in the area of data fusion with partial estimators. We have a multiple parameter case global estimating, multiple parameter case time series forecasting. Then we have wireless sensor network. We have distributed estimation, and we have optimal linear fusion for multi-dimensional case, and so on. Then we have another type of methods, consensus-oriented distributed tracking, and the nodes are arranged in groups, and each node has a fusion center that runs an independent filter, and then we exchange. And then fusion centers reach a consensus, different methods for data aggregation and performing consensus, and benefiting from the network cooperation in terms of performance and robustness and resilience to failure. But the problem and limitation with those methods is that first, the fusion centers are either cores in multi-core workers or machines in a multiple machine setup. Communication most of the times happen on wired platform, and delay is considered negligible, which is not a reasonable assumption under other networks where delay can be significant. Also, another problem is synchronization, which is not as easy to achieve in under other situations. So regular distributed inference methods may not be suitable in general for under other scenarios. So the goal of this paper is to introduce data fusion methods when delay in communication between the partial estimators is negligible. Here we focus on minimum mean square error global estimator, but the framework is general, can be used to combine any type of unbiased partial estimate. So the scenario, as you see here, we have a network of sensor nodes. They measure the strength of the field generated by moving objects and then communicate those measurements with the fusion center in a random access manner. So the total observation area is divided to design units, and each of the design units has a fusion center that runs the column filter. It can be in general anyway, estimation. The neighboring fusion center communicate with each other, and we don't make an assumption about how this zoning basically happens here. It's just it can be in any way. So the method is general, doesn't depend on the way that the zoning is happening. So after a state fusion, these partial estimates which basically combine to get together to basically come up with a general estimate that which to have a design which is scalable across the large area without increasing in complexity. So yes, we as I mentioned, we take into account that when a fusion center receives the estimate from the others, that estimate may be outdated. So we are basically thinking how we can use that outdated information. So the system model, we have a xk is a state vector. It can be location or velocity or acceleration, basically any parameters. So we assume that the location of objects follows a stationary uniform process with the density rho objects per meter squared, and each object emits a signal, and then the signal decays based on the signature function that which we assume is known, and the objects not cooperate with each other. Sensor nodes are distributed uniformly with the density rho s nodes per meter squared, and so at time interval k, the received signal is vkn, which we have it here, and this dk is the distance between the mth object and end sensor at time k, and so on. Fusion center collects the packets, interval time c, which is the collection interval, and then these intermittent observations are used as input to tracking algorithm to estimate the location of the objects. So xk, the state of system at time ktc is shown here. TC, as I said, this is collection interval and the maximum number of objects to be tracked. And here we consider a simple linear state vector, basically evolving with time, but generally it can be non-linear. A is the state transmission matrix, and Q is the process noise. And fusion centers basically try to make the estimate based on the set of the observation that they receive. And some of the observation may be lost to noise and interference. And we use the fusion center use the intermittent observations to estimate the state of the system. So the fusion center, the fusion methods, the goal is to combine this partial estimates that each of those fusion centers have, and in a manner that the performance is as close as possible to the global estimator that has access to the old information. So for the optimal linear minimum mean square fusion rule, you know this general expression you see here. So one thing we perform here is just we do the overwriting, means that whenever we reach the consensus, basically at the end of one interval, we overwrite it back to the state vector of each fusion center. So the state vector is then used to initialize the next round of estimates. But the problem is that with this, we have observed that this overwriting process basically offers improvement in performance in terms of mean square error. However, there's a problem with that, which is it requires fusion centers to wait for the state vector of the other fusion center before running the next round of estimation. So this delay is not negligible with respect to the collection interval, especially in underwater situations. So we need a proper adjustment for basically using those outdated estimations. So one of the way we perform it because of fusion with delay and wait, it's basically in this case, as you see, we have shown two partial estimators. In general, can be anything, but so here at the collection interval, we see the TD, the time delay, is significantly larger than the collection interval, and the way it works is that we fusion center waits for the feedback. So this is the most straightforward way to solve this issue, to wait for to receive all the information from the neighbors, and then we combine those information and come up with the final estimate. So fusion center collects the observations during TC, updates its estimates using whatever final state it has at that point in time, and then exchange those estimates. But the problem, TD here we assume that the delay is a factor of TC, but in general, just to make it easier for understand, but in general it can be anything. So the fusion center has accurate information about the state of system TD seconds ago. So there's this delay. So this information basically constitute the final estimate that will be used at the end of the next collection interval. The equivalent for this is to basically use the change the transition matrix to A to D plus 1. So whatever the delay is in terms of the number of collection intervals, we basically raise the A to D plus 1 to find the equivalent state transition matrix. But another problem with this method actually is the limitation of this method is that the communication between fusion centers should be synchronous, which is not necessarily easy to implement. So because of that, we have another method we call it soft fusion with predicting go, and as we said, for the soft DW, the problem was the waste of resources, and we have to wait for a substantial amount of time to basically make sure that every local estimate is received by all fusion centers, and then perform the aggregation. One solution to solve this problem is to give a proportionally less importance to the outdated estimates, or as you see in this picture, basically equivalent would be to that the estimates basically we make a D-step prediction in each of those estimates based on the basically the system information that we have, and then we use those predictions in the fusion. So you see here the algorithm for the prediction. So the inputs are X hat K minus T, which is the local estimate of the L fusion center at time K minus T, and also covariance matrix for all of the partial estimators. And then we for each of those partial estimators, we go ahead and use those outdated partial estimates to basically predict the current value of the state vector and the covariance matrix. And then basically at the end of it, we have an estimate for the basically outdated estimate, if I wanted to put it in this way. So so you see in equation 7 how the final estimator we calculate and then basically perform the overwriting, and so which is equivalently for simplicity 8 and 9 shows how we basically can come up with the XK double hat L and the covariance matrix estimates at time K. So we show two numerical results here. The first one is mean square error as a function of delay when the number, the density of objects is fixed here, 5 objects per square kilometer, and TC is 1 for different SNRs. And for the benchmark, we showed also the no fusion basically results, and then we don't perform any fusion methods. And the average speed of the objects is 5.1 meter per second. So as we observe here, and the delay is small enough, soft DW outperforms soft PG, and both of them are significantly better than when we compared to the benchmark when we don't have any fusion method. So if you want to consider the sources of error for each of these methods, for soft DW is the increased process noise covariance. As you see here, Q prime is basically bigger than Q in positive definite sense. And for the soft PG, the source of error is the prediction process. So depending on which of these sources dominates, one method perform better than. But in general, for small delays, it's better to use the soft DW. But as also we mentioned, the output requires synchronization between partial estimators, but soft PG basically has an advantage that you don't need any synchronization. And also, we see here the basically mean square error as a function of the density of objects when the delay is fixed. And one thing that we have to take into account is that soft DW provides new estimates every TC plus TD, but soft PG basically generates estimates every TC. So that is another advantage of soft PG. But again, as we see, basically at this value of delay, soft DW performs better across different values of objects per density of objects per basically object per kilometer squared. So the performance of PG, but as we see here, is almost independent from the density of the objects. Why the mean square error of soft DW increases slowly with the object density. So in summary, we considered the issue of delay in acoustic sensor networks for object tracking. So we introduced two data fusion methods for combining partial estimates of the local fusion centers. In the first method, fusion center exchange the state vector and covariance matrix and wait until they all the fusion centers have the information from neighbors, and then we perform fusion and produce the final estimate. In soft PG, the fusion center constantly update their estimate based on the latest observation and fuse it with the most basically recent estimates. Each of them has different advantages and disadvantages. Soft TW requires synchronization and has better performance at lower values of delay, but soft PG doesn't need synchronization and perform better large value of delays. Both better performance with respect to the no fusion methods, and they have basically simulation shows that even at the delay values as large as 10 seconds, we still have they maintain good performance. Thank you, and do you have any questions?
Thank you very much. Questions from the audience?
The video.
Yep. Oh yeah, I see. Raul has a question. You unmute yourself, Raul? Or I can read it for you.
Okay. Yeah. So my question is that you use the received level to estimate the distance as the first estimator here, and that is not very robust because it's hard to achieve in practice that you know the propagation function. So I wonder if but the fusion principles are interesting. So I wonder if you try using the same fusion principles with other location estimators, for example, using time delay-based ranging or bearing estimate-based cross-fixing.
If I understood the question, so yes, the first question is yes. We assume the signature function is known, which may or may not be a reasonable assumptions in practice, but also it doesn't depend. The method doesn't depend on measuring the estimate. It can be time of arrival, time difference of arrival, time of arrival. It can be basically anything. Any estimation method even can be used instead of a Kalman filtering, and the focus is basically on the fusion part in this paper when the delay is not small and negligible. But as I said, yes, any estimation method with it can be RSSI, it can be time difference of arrival, or it can be even delay spread for non-underwater acoustic application. And as I mentioned, it's very similar to the problem that we have in the statistical signal processing for wired. And we want to infer parameters of model from a large data set and break it down to that. And in almost all cases, the assumption is that delay is small, but we can apply the same methods to those cases as well. So, yep, if I got the question right.
Okay, thank you.
I have a quick question. It's more like not particularly a question on the presentation, but have you considered looking into like message passing, consensus-based message passing instead of fusing to get rid of, asynchrony, the problems that comes through asynchrony?
Yes, we basically consider as I mentioned in the presentation, data aggregation methods. In general, we can. I can say it in this way. It's more as if I understood that right. In data aggregation, basically, we mostly in the multi-hop situation, we are looking at like a function that we apply in at local nodes that basically minimizes the communication between the nodes. But here in our case, we basically are more focused on the delay part of the issue. And the estimation part is basically, or how we aggregate the data that is originated from each of the sensors is not basically the point of this paper. So yes, we considered that data aggregation, but basically you can replace any of those methods here for this estimation parts. But in that case, our sensors do not cooperate with each other. They only communicate the measurement to the fusion centers, and all the decision is made on that point. But in general, you can, if you want to see it in that way, you can consider fusion centers as the sensors of the next higher. If we look at it as a hierarchy, then at the bottom is the sensor, and then fusion centers can be considered as the next level in the hierarchy, and then you can apply each of those data aggregation methods. But again, as I mentioned, it's just mostly about how the delay affects the fusion centers, and the application that is mostly assumed that this delay is negligible in basically breaking down the data sets and the intermittent observation to local, basically partial estimators, and then how to combine it in an efficient manner, and how they make the predictions of the outdated estimates. So,
Georgios?
Yep.
Do you have a particular message passing algorithm in mind that you think would be good for this?
Not right now.
Not right now. Okay, that's what I meant offline. If you think about it later, just email me, please.
Absolutely. Yeah, absolutely.
Thanks.
Anybody else wants to unmute and ask directly? So I think, yeah, we're a bit over. Your call.
Are we good? Thank you, George.
Yeah. Thank you very much.
Thank you. So I think this kind of wraps up the day, the first day of UComms 21, and all of a sudden I saw a few more familiar faces popping up. So I would not let this go without a shout out to the UComms honorary chairperson and founder, John. How are you doing? Anyway, I would like to thank everyone that...
I apologize for showing up late, guys, but I have a compulsory Norwegian class, and I get my wrists slapped if I don't show up for my Norwegian class. And so that's meant that I wasn't able to come as early as I might have wanted to. But tomorrow I hope to hear more.
Great. I think at this moment, it's just the time to say thank you for everyone that logged in, that connected, that gave great presentations, to the chairs that conducted the 2 sessions of the day. So although, as I said in the beginning, this is a kind of a challenging and very far from ideal setting, considering what we are used to in UComms, it's a matter of trying to make the most out of the situation. So thank you again very much. We have a big day tomorrow also with very interesting talks lined up. Tomorrow, Costas will run the show from the CMRE side, and we'll have 3 different sessions running. So unless anyone wants to take the stage, say something, I will call it a day for today. So I call it a day. See you everyone tomorrow. Thank you very much. Thank you for sticking around. Bye.